Okay, welcome to day 5 of ST4 2020. The first speaker of the day is Biswajit. He's going to give his last lecture on soft theorems. Over to you, Biswajit.
Yep. So I think it's lecture 6. Okay. So let me first just briefly recap what we have done last day. So yesterday what we have done, we started Feynman diagrammatics analysis and tried to derive subleading soft photon and soft graviton theorem in 4 space-time dimensions. Basically, we have in detail, we have done the soft photon theorem, and then the extra subtleties which usually arises in the analysis of soft graviton theorem, we explained, and then also given the result for the soft graviton theorem up to the subleading order in expansion. And what we have seen is that at the subleading order, now due to this loop correction, the soft theorem is not goes like omega to the power 0 if omega is the soft energy, but it turns out to be logarithmic of soft energy. And then the coefficient is completely universal, determines only in terms of initial and final particles momentum. Now, and then in the earlier lecture, what we have shown is that comparing the energy computation or energy flux computation from the soft theorem's classical limit and independent classical computation of the waveform, we have related the soft factor to the waveform structure. Also there we have seen that if we try to solve, say, Maxwell's equation or even Einstein's linearized Einstein's equation, and then we try to see what will be the waveform structure at large distance, then we have seen that the radiative mode of the waveform can be directly written as a Fourier transform of the energy momentum tensor. So the relation what we found, now there we have assumed 8 pi g equal to 1, but now I am bringing back all my 8 pi g factors. So now now the relation turns out to be that if you do a Fourier transform in the time variable of the trace reverse metric fluctuation, that turns out to be 2g upon r times if e to the power times e to the power I omega r, which is basically extra phase factor, and then this t hat of mu nu of k, which is basically Fourier transforms of the energy momentum tensor, which is written here, the full Fourier transform. And the e tilde mu nu is basically, if you in the time variable, if you do a Fourier transform, then this is e tilde mu nu is defined. And here x vector is basically r n hat. R is the distance from the scattering center to the detector, and n hat is the direction along the detector. And k mu turns out to be energy of the graviton or gravitational wave, and then there is a 1 comma n hat. N hat is the direction to the detector. So this is the relation which we have established earlier for the electromagnetism case, and it goes similarly for the gravitational case as well. And we have written down the expression here only in d equal to 4. So now it turns out that we can determine the long wavelength gravitational waveform if we just can determine the Fourier transform of the energy momentum tensor. This is broadly speaking. So what I will do next is basically try to consider as a classical scattering process where some macroscopic objects are involved in the scattering, and analyzing the asymptotic trajectories of this as a scattered object, we can write down what will be the form of the energy momentum tensor, and then we will take a Fourier transform of this energy momentum tensor. That energy momentum tensor may involve gravitational energy momentum tensor as well, and then taking Fourier transform of this energy momentum tensor, using this relation we can relate it to the gravitational waveform. So this will be the goal. And the thing is that so what will be the strategy to, so our goal will be to find okay for, so now I will consider all the outgoing particles momentum are positive and incoming particles momentum are negative. the opposite convention for the amplitude prescription what I have used. So here I will follow that k mu to go omega comma 1 hat. Just one small point, just a convention change which I am making here. And I want to analyze for what will be the expression of this energy momentum tensor for small omega. So small with respect to what, that when I will describe the or setup, then I will explain omega, which is the frequency of the gravitational waveform. So small compared to what, that I will explain. And the prescription is that one thing I want to say, that like we are working in a unit where c equal to 1, and in that unit what you can see is that basically g, m and omega, this turns out to be dimensionless quantity. Where m is basically the finite energy particles mass or momenta, equals mass say, and omega is the frequency of gravitational radiation. Change the color to white. Okay. And what it is telling us, that if we want to analyze the small omega expansion, this is same as a perturbative expansion in omega. Sorry, perturbative expansion in G. Right, because GM omega will come in like in a expansion, as a expansion, since it is a dimensionless quantity, so it will appear together in the expansion. So if we are interested in the omega expansion, that turns out to be the expansion in the power of G. So this perturbative expansion works, and you can think of this is also iterative expansion. Like if we have a order G corrected metric, then using this we can correct the trajectory, and then using this we can get the order G squared metric fluctuation. So this perturbative basically goes to like a iterative prescription. So what we have to do is that we have to iteratively solve iteratively in power of G, Einstein's equation, to find metric fluctuation, and geodesic equation to get the corrected trajectory of the particle or corrected trajectory of the macroscopic object. So this we have to do iteratively in a expansion in expansion of G. And since G and omega comes together, so basically that will also give a omega expansion. Okay, so up to now, is there any question? So then let me proceed and give the setup. So what we have seen is that if we are interested to extract the log omega piece, which basically takes care of the long range gravitational interaction piece. So basically if there is some kind of strong gravitational interaction or other kind of interactions, those happens in a like localized region of space-time. So those will not affect to our logarithmic term. So the setup which we'll consider is that some particles are coming in, say with momentum p1 prime P2 prime to PM prime in a region R, and they have all complicated strong interaction inside the region R, and they go out in number of objects. And this region R has a space-time the size of length L, say. And the choice of the region R would be such that, so region R choose so that outside region R only long range gravitational interactions present. Okay. So this is the setup which we are considering, that we don't know what is happening inside R. Maybe some particles are coming in, they splits into like some objects are coming in, they splits into many objects, or maybe two objects are coming in and they fuse together. Many things can happen. And so we will not consider this region. Only we are interested in the asymptotic part of the scattering process. So that only outside we will choose this region R such that outside this region are only long range gravitational interaction present. All the local strong interactions and complicated process happens inside this region R. So what that will do is that after choosing this region R, then the question what we can ask is that determine E tilde mu nu omega comma x vector in a frequency range when omega is much less than L inverse. Okay, because L is the like space-time size of this region R, and then basically if we are interested in a frequency range which is much like a frequency which is much smaller than the L inverse region, then that part of the frequency we would expect would not be affected by whatever the complicated interaction happens inside the region R. And this translates to the fact that if we do a Fourier transform in the omega variable, then this translates to determining E mu nu of t comma x vector in some retarded time u, where u is much greater than L. Okay, so this is basically a consequence of the first condition, that if we are interested with the wavelength which is much greater than the L, which is the space-time this space-time length of the complicated region where the complicated interaction happens, then the time scale associated to this process after which we can trust our result is basically when u is much greater than L. And obviously if you put a detector at distance R, say from the scattering center, you put a detector here and say the detector distance is capital R, then obviously that will put also a bound that only the frequency range what you can consider is R inverse, the omega should be much greater than R inverse, because like if the omega is turns out to be smaller than R inverse, then what happens is that this kind of gravitational wavelength become very large compared to R, and you cannot observe by putting a detector at distance R. So this is the setup which we want to analyze and try to derive the gravitational radiation. Okay. So since outside this region R, we have only like there is only long range gravitational interaction present. So probably structure of the objects and how the scattering region R is, all these things would not be important to us, and we can well approximate our scattering process outside this region R by this simple action. So the Einstein-Hilbert part, and then n number of outgoing particles. And m for m number of incoming particles. The trajectories I will call by x prime a sigma, nu d sigma. And what this sigma equal to 0 corresponds to, sigma equal to 0 corresponds to the proper time when the particles enters or exit the region R. Okay. So let me tell. So this is the action. This is the Einstein-Hilbert path, and this is the like minimal coupled trajectory equation for a particle, world line action of the particle. And this is n number of particles are outgoing. That's why the sigma runs from 0 to infinity, because at 0 basically the particle exit from region R, and then at infinity it reaches the asymptotic point. And like for the incoming particle, it starts from minus infinity, and at sigma equal to 0 it enters the region R. So then if you just vary this equation, what we will find is that the usual known Einstein's equation, but I will write in a different thing, that I will take the square root g within the definition of the left hand side of the Einstein equation, and then this will be matter energy momentum tensor, and this matter energy momentum tensor Tx mu nu of x, we just vary with respect to the metric and define it not with the square root g, in a sense delta s upon delta g mu nu only, without taking the square root g. What we will find is that and similarly for incoming particles. Let's call their mass to be m prime a. Probably I have written here still ma, but let me call m prime a. N minus infinity to 0 d sigma delta 4 x minus x prime a sigma d x prime a mu d sigma and d x prime a nu d sigma. Okay, so this is the matter part of the energy momentum tensor, and that is the Einstein's equation which we'll consider. Now what we will do, we will substitute that g mu nu to be eta mu nu plus 2 h mu nu. Let me call here in place of s mu nu that h mu nu, or you can call it to be s mu nu as well. and then we will define the trace reverse metric fluctuation E mu nu to be H mu nu minus half of beta mu nu H rho rho. And then what we will do is we will substitute this expression in the Einstein's equation in the left hand side, and then we will keep only the linearized part of the E mu nu piece, and rest of the starting from the quadratic piece of the E mu nu, all these things we will take to the right and define total energy momentum tensor, which is basically sum over this matter energy momentum tensor plus the gravitational energy momentum tensor. And then that we will solve in iteratively in order of G. Okay. So then up to linearized order, it turns out that in Didonder gauge, total energy momentum tensor T mu nu, that is total energy momentum tensor T mu nu has the matter part, and plus some gravitational energy momentum tensor which we are denoting by TH mu nu, and this TH mu nu is defined as, if you take basically take the starting from the quadratic to the rest of the piece to the right, then it has the structure like so. This was the whatever they are in the left hand side with a minus sign if we take to the right, and then we have to subtract from here the linearized part. Okay, so this will be the gravitational energy momentum tensor. So is there any question up to this point with the setup? Okay, if not, let me proceed. So that is one of the thing, and the other thing is that, like, if we start with the asymptotic trajectories of the particles to be straight line, and then we want to correct it more and more, with the thing that if we have a corrected metric in each step, so we have to solve the geodesic equation of the particles to correct its trajectory too. So we have to solve also, let me give all the inputs. So we have to solve the geodesic equation of the particles. Equal to 0. Okay. Now, to analyze the incoming and outgoing particles in the same footing, we will use some compact notations. So the notations which we will use is basically, if for the incoming particles, we will treat them as also outgoing particles using this convention, that prime A, and then the velocity of the n plus h particle is prime A and prime A for A equal to 1 to m, which are the basically incoming particles. So incoming particles momentum, mass, and velocity could be identified with the outgoing particle, like considering that those are n plus a outgoing particles. And then what happens is that then for also incoming particles, the sigma also runs from 0 to infinity. Okay, so then basically the analysis will become simple, and at one go we can analyze the incoming and outgoing particles. Okay. So we have to basically expand each of our metric and the trajectories in power of g, and then we have to iteratively find out the like fixing a power, like if you, okay, so what happens is I directly power the coefficient of the G expansion for the trajectories and the metric both. So for that, let us consider that the asymptote to start with, we have asymptotic trajectory of the particles which are straight line, and there is some corrections. So say x mu sigma equal to RA mu plus BA mu sigma plus some corrections y mu sigma. For now, for all a equal to 1 to m plus n, and sigma always runs from 0 to infinity with the convention what we are using. What this RA is telling us is that in this region R, if some particles are going out, say at sigma equal to 0, the particle's position is determined by the RA, right? So in a sense, the earlier what I tell is that if some two going to two particle scattering is happening, you can think of this RAI to be the impact parameter, and RA0 is basically the time delay between the two particles. And VA is the asymptotic velocity of the particle, which is PA mu upon its mass, and YA mu is basically correction, which you have to find solving geodesic equation in each order of G iteratively. So then we can expand that all the what we need, all the ingredients in power of G, say expand that T hat mu nu of K in power of G K, where delta R of T hat mu nu of K turns out to be order G to the power R. And then with this TR, if you compute with this delta R of T, if you compute the metric fluctuation and expand it, we'll find that it will start from, so let me give the notations full. So tilde mu nu omega comma x vector, where this turns out to be order G to the power R plus 1. So it starts with order G, and then let's expand this corrected trajectory of the particle to also order expand in order of G. Sigma and delta R of YA turns out to be ordered G to the power R. So is there any question? So if not there is question, let me proceed that let us start with the case that the asymptotic trajectory is straight line. Sigma, okay, and for that let us find the first leading order in energy momentum tensors Fourier transform. So that basically translates to d4x summation. So let me, with the expression, if we just substitute and use the delta functions, then finally what we will get is
Biswajit, the screen seems
yes.
to have frozen.
Okay. Sorry, my Zoom somehow. Can you tell the password and ID if you have?
Yeah, the ID is 846
846
9764
9764
6962.
6962.
Password is 806070.
80.
6070.
Okay, thank you.
Just a quick tip. In the Zoom monitor itself, there is a I button, info. If you click that, you can see the meeting ID and password.
Okay. Okay, so up to now, is there any question? Then I can take, or I'll proceed. So the main strategy is that, like, since Gm omega is dimensionless quantity, so expanding in omega turns out to be expanding in power of G. That's why we can do the iterative expansion and in order G, and the strategy will be iteratively to correct the trajectory starting from the straight line trajectory, and then find the corresponding metric, solving the linear distance equation, and then with this metric correct again the trajectory to the next order in G. And we can proceed for like up to subleading order and try to derive the log omega coefficient. And possibly, if we can do much more higher order, we can also extract the higher powers in omega expansions also. Yes.
I have like a naive question. So is this like a convergent expansion? Like when you do this expansion?
Okay. So first, yeah. What is that? Yeah, actually, we don't know whether it is a convergent expression because we cannot actually extract all the terms. Right. What happens is that, so what I have told is that, like, there is in omega expansion. So suppose the leading order is 1 over omega, which it turns out to be G upon omega.
Okay.
Some factor. Then in the subleading order, it turns out to be G square times log omega. Okay. Right. So with some factor. And then with this, there is some omega to the power 0 piece also in G square order, which we don't have yet. We cannot, once we get log omega. In the next order, if you try to do, it will become G cube. And then there will be like omega log omega square. Okay. And then we don't know the expression for the coefficient of omega log omega and the coefficient of omega. These terms we cannot determine very easily. Okay. So we don't have even all the terms in the series expansion, only the leading non-analytic structure of each power of G we possibly can determine.
Okay.
So that's why we cannot even make comment that it's convergent or divergent.
Biswajit?
Yes.
So you are expanding in the soft momentum omega, but the total energy momentum tensor is for the whole theory. That is not only the soft part.
Right. Total energy momentum tensor is for the matter and for the gravitational, the whole theory.
Okay.
Yes. Because you know that though I want to find the, like, I have to solve the linear distance equation, and in the right hand side there is the full energy momentum tensor is sitting. Then after finding this E mu nu of x, then I can take that large radius limit to find out the radiative mode, and I can take the small omega like limit to expand in small omega expansion kind of thing. But since the construction, we have observed that the small omega expansion is tied up to the G expansion. So that's why from the beginning, we know that how to do this iteratively. Okay. So at leading order, it turns out that if you consider these straight line trajectories and substitute in the energy momentum tensor and do a Fourier transform, VA nu, and you can evaluate this in d sigma integration for this term. And since you expect the energy momentum tensor should not diverge at sigma equal to infinity, so that will fix your I epsilon prescription for this k dot VA. Because you want at sigma equal to infinity, this result should be finite. So that will fix your I epsilon coefficient for this k dot VA part. And it turns out that VA minus I, so you need a minus I epsilon for the convergence of the integral at sigma equal to infinity. Okay. Now this is what you find the leading order energy momentum tensor. Then using this leading order energy momentum tensor, you try to find what will be the leading order metric fluctuation. So that would be the next step. And see, this is ordered g to the power 0, as we also in the expansion we mentioned, I think, that it starts with r equal to 0 to infinity. So delta r is ordered g to the power 0 delta 0 piece. But now since the linear resistance equation contains 8 pi g times energy momentum tensor, so the first leading order expression for the delta r, which starts with r to the power 0, that has a g to the power 0 plus 1, which is order g because of this 8 pi g factor. So let me proceed then with this leading order energy momentum tensor expression to find the leading order metric. So the trace reverse metric. So say there are all particles scattering. Say for a particular particles motion, what will be the metric fluctuation? So the trace reverse metric fluctuation for at leading order for particle B motion, you just solve the linear resistance equation. So at leading order g to the power 0, the energy, there is no gravitational energy momentum tensor. So the matter energy momentum tensor, whatever we have computed here, this is the full energy momentum tensor. That's why I have not put in here any x, but you can put x also. The delta 0 of TH is 0. So then what you will find is that you use reiterated propagator to compute it in momentum space. This basically turns out this is the momentum space retarded propagator, which we have introduced earlier for particle B motion mu of L. By this GR of L we have introduced, which is basically L naught plus I epsilon whole square minus L vector square. Okay. So you don't have to evaluate the integral, you just keep as it, keep just as it is, and then you from there you compute what will be the leading order crystal connection for this metric due to the bit particles motion. Okay. And then if you once find this thing, you just solve for delta 1 of YMU sigma, which is the correction to, which is the first order correction to the trajectory of the particles from the straight line trajectory. So basically solve sigma square minus delta 0. So minus sum over all the particles B not equal to A. And if 8 particle is incoming, then you choose all the sum, if the bit particle is also incoming or outgoing, or sum over outgoing. But if you even don't choose this thing, finally it will turns out, if you once you do the integration and all this thing, only you will get the contribution that only outgoing particle affects the trajectory of the outgoing particle for the outgoing particles motion, and incoming particles motion affects the trajectory of the incoming particles motion. So I'm not that's why putting any constraint of the incoming outgoing, but you can do that. And then sigma and then VA nu VA rho. You have to just solve this equation to find the correction to the straight line trajectory. And you see what will be the boundary condition. This is a second order differential equation, so I have to give the boundary conditions. And the boundary conditions is basically asymptotically you will expect the trajectory at straight line, and whatever the correction is the correction that drops out, like we have seen when we have done the similar kind of analysis using affine parameter sigma. It turns out that the correction basically turns out to be log omega, the correction to the trajectory, and its velocity is 1 over, sorry, log sigma, velocity is 1 over sigma, so sigma going to infinity vanishes. So you expect that asymptotically its velocity is constant. So sorry, delta 1 y mu sigma d sigma goes to 0 as sigma going to infinity. And the other thing is that since we have defined that RA is basically the position where the particle starts its motion from the region R, so there delta 1 of y mu sigma is precisely 0 at sigma equal to 0. So with these boundary conditions, you can find what will be this delta 1 y mu sigma is, which is the first order correction to the straight line trajectory of the asymptotic scattered objects. Okay.
So Biswajit, this
Yes.
fact that the outgoing particles are unaffected by the incoming particles and vice versa can also be understood from the light cone structures, right?
Right. If you do in coordinate space, it is like very well understood from the light cone structure. But in momentum space, you can see if you just even don't fix that it is incoming or outgoing, fix all B not equal to APs, you can see that in the momentum integration, when you do finally from the pole deformation, you can see that it will not be affected if incoming particle is moving, outgoing particle will not affect it.
And that's specifically where the retarded propagators become important. For example, if you had these Feynman propagators,
right.
Then there could be some overlap.
Right. That is what happens for the quantum case. The overlap happens for incoming and outgoing.
Okay, thanks.
Then so once you find out this delta 1 y mu sigma, you just go and now find the subleading order correction to the energy momentum tensor. Right. So you now find, earlier we computed delta 0 of t hat, now we are computing delta 1 of t hat. Now we have the inner, like this is basically order G, and it contains a gravitational energy momentum tensor also. So first we are computing the matter part. So if you just see how the matter part looks like, using the expression of the matter energy momentum tensor we have given and using the expansions of the y mu, what you will find is this sigma piece. Okay, so this term comes from the expansion of the exponential. There you have to put a trajectory and you expand in power of g, since it is k dot b is constant, delta 1 of y is order of g. So this comes from the exponential, and these terms comes from the dx a mu, dx sigma, dx nu, d sigma piece if you keep up to order g. And now you have all the informations for the delta 1y and derivative of the delta 1y from the solution of the geodesic equation. You just substitute it here and do the sigma integral, right? And what you will find that if you, after doing all these things, but you'll find that this integration, if you try to analyze that in which region it contributes to logarithmic of omega. So, or omega is basically the energy of this k. So what you will find is that in the integration region, when L mu is much greater than omega and much smaller than Ra minus Rb inverse, which is in the same order of the space-time length of this region capital R, which is the L inverse. So only in this region what you will find that this contributes to log omega. Okay, similar to the diagrammatics analysis which we have explained, the same region there appears, where in place of L inverse, there the particles momenta inverse, particles momenta appears. But here, in a sense, you can think of this region L where the all complicated interaction happens, and this L basically acts as a UV cutoff of your theory, like UV cutoff for the long-range gravitational interactions. And then basically you have to integrate out the loop momenta L mu, which runs greater than omega and less than L inverse. Then you can analyze this integral structure after substituting all the expressions of delta YA, and finally what you will get from the region omega turns out to be minus I times the tree-level subleading soft factor, which we expected, rho minus PA rho del del PA nu times whatever we have shown the in the kg decomposition, basically the exponentialized factor of the k, whatever we have. But now only the classical part, in a sense, if you just have the expression for the k part and you evaluate from omega to L inverse region, but now with the replacement of the Feynman propagator there by the retarded propagator, the expression what you have, that will turns out to be here. But with this, there is extra part, which will, if you just analyze this thing, you will find there is extra part for the matter energy momentum tensor. You have mu AGR classical. And that piece you will expect this is not gain invariant by itself. So also you have to analyze the gravitational energy momentum tensor, and you will expect that this piece should cancel from the gravitational energy momentum tensor. Okay. So this is the same similar analysis, the diagrammatic analysis we have. You can combine this result and you can see that the exact matching with that result. So now if we understood the matter part in the subleading order energy momentum tensor, now we can try to see how the gravitational part of this subleading energy momentum tensor we can evaluate. So yes.
So just to connect with what you talked about earlier about this kg decomposition and the region of integration. So in the quantum field theory, you had for the soft graviton contribution, you had the region of integration from omega to higher, omega to infinity, right? And that gave this log omega. But there was an additional piece. So that region of integration probably is from 0 to omega.
Right, from this IR, the detector distance, which is R, so R inverse to omega, that will come from the gravitational energy momentum tensor. So, okay. Because you know there it comes from the like there it comes from the 3 graviton vertex diagram, right?
Right.
And 3 graviton vertex diagram you can think of nothing but here basically the quadratic energy moment, gravitational energy momentum tensor, which is quadratic in H, because in the action that will be coupled to the H mu nu.
Right. So there are correspondences between this classical analysis and the quantum kg decomposition that you did.
Right. And like if you have to just replace the Feynman propagator by the retarded propagator.
Okay. Yeah. Thanks.
Yeah. So that is also one of the observations which I mentioned earlier. So now we also have to analyze the gravitational energy momentum tensor, because that also now contributes at order G. And tensor. Thus it starts contributing at order G. And this turns out to be the quadratic part of the metric fluctuation you have to analyze, and that contributes to order G. And that expressions in momentum, if you do a Fourier transform, it basically takes this simple form. So what this function AP is basically, see in the quad, like since you are getting this thing from square root GR, so there two derivatives are involved on the metric fluctuation. So these two derivatives can operate on, like both can operate on the same edge, or one of them on first edge and the second of them in the second edge. So that will be basically have the structure, which is basically some momentum structure, which is K minus small l, K minus small l, plus with some index structure with L into L in K minus small l. So some index structure, say there are some low range index sitting there corresponding to this mu, nu, alpha, beta, rho, sigma vector. So this is a long expression, but you can read it out just expanding the energy momentum tensor up to quadratic order in H, or also you can read it out from the three gravitational vertex, taking one of the H mu nu completely out of the energy momentum tensor definition. And the rest, analyzing this, you can also find out this piece. Okay. So, but the thing what I want to mention is that this is quadratic in the momenta. Now you see that already we have shown that how this part looks like. This part has a structure like GR of L upon 1 upon PA dot L minus I epsilon. The L dependence is only here with some sum. And it has also similar kind of expression, GR of K minus L, some B particle with PB dot K minus L minus I epsilon structure. Okay. And so basically you see that in which region this contributes. So you can see that there is 2 GR of L factors is there and 1 over L here. Now you see that there is, if you see the, suppose in the region of integration which is L much greater than omega, you will have from 2 denominator of L from the GRL, 2 denominator of L from the GR of K minus L, 4. And then from PA dot L you will have a 1 denominator L, and the PB dot L, PB dot K minus L, they will be 1 over L. So 6. And from the numerator F also you have a quadratic piece in L. So this will also contribute to log omega, because that basically goes like D4L upon from LL from the numerator, and from the denominator it's like L to the power 6. So this region also can contribute to log omega. Also if you analyze that L much less than omega, that region also contributes to log omega factor, and that you can see that 1 over this GR of K minus L will give it 1 over K dot L in the leading order when K is greater than omega. And there also you can see that that also goes like D4L upon L to the power 4, starting from, sorry, upper limit is omega. So there is 2 integration regions in the gravitational energy momentum tensor, which one have to analyze, and both contributes to logarithmic omega. But the difference between these 2 regions is that when L is much greater than omega, there the log omega cutoff is determined like log omega times something for the dimensionless, and this cutoff is determined by the region of the region R size, which is L. On the other hand, when like loop momentum is smaller than omega, it will be cut off by the detector distance R. So let me then say in which regions what contributions you will get. So what happens is that when loop momentum is smaller than omega, this region, if you try to analyze, you will get contribution from gravitational energy momentum tensor to be the phase factor, whatever we have multiplied to the leading soft factor, what we have shown, which basically takes care of the time delay and the gravitational backscattering part, which we explained earlier. Outgoing particle only, and then the leading soft factor. A dot K. And if you try to determine if you try to analyze this gravitational energy momentum tensor when L mu is much greater than omega, that would, you can see, cut off by L inverse. And if you try to analyze this region, what you will find that leaving this log omega piece, whatever you know, like whatever you will get to cancel this extra piece, whatever you have in the matter energy momentum tensor, the minus I summation over A equal to 1 to M plus N P nu del P mu AGR classical. That is what you will find. But with this, you will find another piece. Let me call it radiation piece. Okay. And this will basically tells us that actually, since you are analyzing the gravitational energy momentum tensor when the loop momentum is much greater than omega, so this also contains the fact that if some finite energy gravitons are emitting, which is the hard gravitons, and from the finite energy graviton some soft graviton is emitting, that kind of part is also inside this delta 1 of T hat H mu nu piece. And since those kind of terms already, since those are like the soft gravitational emission from the hard graviton, and those you have already taken into the sum of the hard particles, like suppose if they are outgoing, then inside the 1 to n number of particles, so that part you have to subtract by hand. So the expressions for this gravitational, so I can also explain why this, if you just analyze this thing, you will get the expression for this soft gravitational radiation from the hard gravitons, and the expression basically turns out to be, which you have to subtract by hand. Okay, maybe I should write in a better way so that one can understand it in a clear way why this is radiation from the hard gravitons. So this you can show as epsilon say alpha beta P alpha P a beta upon P a dot L minus I epsilon, and then summation over B equal to 1 to M plus N epsilon star rho sigma P a rho P a sigma by PB rho PB sigma by PB dot small l plus I epsilon, and then L mu upon I times K dot L minus I epsilon. So what it is, you see, this is basically the mod of S0 square. S0 was the leading soft factor, and this is the phase space integral for that. So this basically tells us that the energy radiation, or the number of graviton radiation, and within the energy which is much greater than omega, and this is some real graviton emission because this delta L square and theta L0 is there. So this is L square have to be 0. So this is real gravitational emission, and this is hard graviton because its energy is much greater than omega. And then this is multiplied basically with a soft factor, which is basically telling us that if some hard graviton is radiating with momenta L mu, and if some soft graviton with momenta K is connected to here, then it turns out that the soft factor turns out to be L nu, which is the hard particles momenta, like P mu here basically L mu, and then K dot L minus epsilon. This is the leading soft factor. If some soft graviton of momenta K is emitting from hard graviton of momenta L mu, and this is basically the flux of the hard gravitons with which one have to integrate it out. and that factor appears there. And since this kind of factor already you have taken in the sum over the finite energy particles, so one have to subtract by hand from the gravitational energy momentum tensor. Then you would find that this part of the gravitational energy momentum tensor cancels the non-invariant piece of the matter energy momentum tensor. Then you will get the expected full energy momentum tensor at the subleading order, which is, if you multiply by I, you will give the soft factor times this phase factor also what you have.
Biswajit,
Yes.
So in this expression, is there a logarithmic divergence here?
No. This is linearly divergent. So
right. Okay.
So because you know why this will be linearly divergent physically, because if you decrease the region of size L, which is the region R,
okay,
then there more strong interactions are happening and more hard finite energy gravitons will emit.
Okay.
Right. So that will tell us that basically if you take L to be 0, basically because if it is a linearly divergent, then this will give you 1 over L factor. Right?
Yes.
Sorry, not here.
Next.
Where are you getting here? Sorry. So here see delta L square, basically you can think of like 1 over L square power goes.
Right.
And there 1 over L, and then here 1 power of L in the numerator relative to the denominator. So it goes like d4 L upon L cube.
Yeah.
Right. And then you have to integrate from omega to L inverse. And that gives you 1 over L. And if you take L going to 0, this basically diverges. That is basically telling us that if you like collapse this region R to a very small size, then large number of hard gravitons will emit, and the gravitational energy momentum tensor for this large number of graviton will emit, and from the soft graviton will emit, so it will diverge. So this basically tells us the UV region. Like L is basically the UV cutoff, you can think, and you are taking it to be near the 0.
Okay. Thanks.
Okay. So then basically you sum over all the contributions and substitute the classical part of this K of GR, which you have, and then you can find out what will be the full energy momentum tensor expressions. So let me write it down, because that will help us to describe the gravitational memory. So up to order G, you will find the gravitational energy momentum tensor, the full energy momentum tensor, which has obviously the leading piece. Now I will separate the incoming and outgoing particles with considering Pn plus A to be minus P prime A for the incoming objects, and I will split it up in terms of incoming and outgoing objects. And if you do this thing, the leading part will look like, which is the order G to the power 0. So I epsilon, and then equal to 1 to m P A prime mu A prime mu upon P A prime dot K minus I epsilon. Okay. Then you will have this one piece is log of omega plus I epsilon times L for outgoing particles with some mu nu factor, which is function of PA, PB, and N. N is the N mu, which is basically omega K mu by omega. And also you'll have a log of omega minus F. So there is log of omega term I am telling. Now you can fix what will be the I epsilons also corresponding with this, what will be the I epsilons of this log omega by studying the analyticity structure of these integrals, which we have not shown, just given the result. This I epsilon prescription for these logarithms also will be fixed studying the analytic structure. And then you will have the same function mu nu, but now with the incoming particles momenta, which are primes, and this extra phase factor what you have. And this log omega is cut out by r, the phase factor, which is the detector distance from the scattering center. and then the leading soft factor. Let me call this S0GR. This. And this mu nu b mu nu can be worked out just operating the differential operator on the KGR piece. So this is a long expression, so that's why I have not written it down here. So this will be the structure. Now you see that, so the leading, so you can, what I have shown earlier also explained that this is nothing but the minus I times the soft graviton factor. Right? So you can then identify that if you replace the minus I, this is the leading soft graviton factor and all these things, one can compare. Now what we will do is that we have the expression that E tilde mu nu of omega comma x vector is nothing but 2g upon r times e to the power I omega r times t hat mu nu of k. So this is what we know. And once you have this t at mu nu x, you can just use this relation to find the gravitational waveform in frequency space. Now you do a Fourier transform in omega variable to find in time space how this gravitational waveform will look like.
Sorry, what is capital B mu nu factor?
Capital A mu nu?
No, you say capital B mu nu and capital A mu nu. Am I right?
No, I just told the both are capital A mu nu. Just one is function of PA PB, one is PA prime PB prime.
Okay.
Primes are for incoming particles momenta, non-primes are for outgoing particles momenta. Okay. Yeah. So this A's can be written, like I have not written it down, but you can see this A could be written just. So let me explain how to say. So A's are basically if you just operate this differential operator on this KGR classical first and stripped out the log omega piece, then whatever you will have, this is the A piece, A mu nu piece. This is a long expression, so that's why I have not written it down. Okay. So just want to point out that like the leading power is like 1 over omega and the subleading power it is like log of omega, but now there is log of omega plus I epsilon for the outgoing objects and log of omega minus I epsilon for the incoming, and the phase factor has a log of omega plus I epsilon. So when you do Fourier transforms, depending on this I epsilon, whether it is log of omega plus I epsilon or omega minus I epsilon, it will tell us that whether it will affect the early times gravitational waveform or the late times gravitational waveform, because of the following reason of the Fourier transformation rules. So if you, let me give the results of the integrations, what you have to do if you do a Fourier transforms of d omega upon 2 pi to the power minus I omega u, 1 upon omega plus I epsilon, that turns out to be minus I of theta of u. This is the usual, the theta function definition. And then when you do a Fourier transform of d omega by 2 pi to the power minus I omega u log of, say now you have omega plus minus I epsilon u. So for plus you will get a minus, for minus you will get a plus sign, and then theta of plus minus u into 1 by u plus corrections. Okay. So this is telling us that the log of omega will give, in the Fourier transformation, will give you 1 over u piece. But whether it is log of omega plus I epsilon, then it will affect the u going to plus infinity part of the trajectory waveform, or if it is omega minus I epsilon, then it will affect the u going to minus infinity part of the gravitational waveform. But for the leading piece, which is 1 over omega plus I epsilon, that will only affect if you fix your detector, like, okay, I will tell the detectors also. So that will only give the difference, the change between the u equal to minus infinity and u equal to plus infinity gravitational waveform. So if you use these results of the integration and do a Fourier transform in the omega variable, what you will find is that at u going to plus infinity, your gravitational waveform will look like outgoing particle, A dot n, then minus incoming particle with momentum prime, but then back close the bracket, and then there is a 1 over u piece, which is the tail memory, which usually people call the tail memory. So why I will explain in a minute. Whenever you have this mu nu piece for the particles PA, PP, and N. With this, the phase factor also contribute only at u going to plus infinity. Outgoing A dot n, and then let me call this omega multiplied with the leading soft factor, which is basically nothing but this factor. Okay. So this what you will get at u going to plus infinity, and at u going to minus infinity, you will only find out a tail piece, which is just due to the long range force between the incoming particles. Net turns out to be 2g upon r times 1 upon u, a mu nu, p prime a, p prime b, and n. Okay, and here u, which is the retarded time, that turns out to be t minus r, and with this there is this time delay piece, right, which is the appears in the log r piece in the phase factor. B dot n. So this will be the structure, how the gravitational waveform will look like at u going to plus infinity and u going to minus infinity. So it is telling us that at u going to minus infinity, strictly, if you fix your detector, say at like if you fix your detector at some distance, then at u going to plus infinity, it will change by strictly u going to plus infinity, it will change by this amount, which is a constant piece. And this is what people known as the gravitational memory, or the earlier known Christo W gravitational memory, which basically gives a permanent shift. Since you see the metric is starting, suppose you are starting with a Minkowski metric where you put your detector, and then after the scattering happens, there is a constant shift to the metric at u going to plus infinity. And this, due to this constant shift, now your metric changes to eta mu nu plus this constant shift, and with this metric you have to now compute the proper distance between the mirrors of the detector, and that will change the distance, but that will make a permanent shift between the distance of the mirrors of the detector, and this is known as the known DC gravitational memory effect. So one will find a DC gravitational memory from the leading soft factor or the leading part of the gravitational energy momentum tensor. We're going to do a Fourier transform, which will tell us that after scattering, you will have a permanent shift between the mirrors of the detector, or permanent displacement, say. Between the mirrors, right? But with this, we have seen that there is a 1 over u piece, which is telling us that if you are not at strictly infinity, but you are starting from some large u and trying to going to plus infinity, say, then not only this permanent shift, but you will have some extra displacement, and that decreases in power of 1 over u when you go to going to infinity. And this basically tells us there is a like this is telling us that there is a tail effect in the gravitational memory, which basically tells us that, say, how the gravitational waveform profile will look like. Maybe some transverse traceless piece of the gravitational waveform with time t. So up to some time you cannot apply this formula when you up to some time scale which is order L, where all the strong gravitational things happens. So all the quasi-normal modes and quasi-normal mode and all the others when the black holes are merging, strong gravity is present, those kind of things will be present here, and that part would not be determined by the soft graviton theorem. After that you will have at you going to infinity you will reach a permanent shift. So if you start with eta mu nu, you will hit a permanent shift which will be determined by the leading soft graviton factor delta 0 of E transverse traceless ij piece, but you will have a tail piece which goes like 1 over u. Okay, so this is up to order G what you will find. If you try to do the iterative order in a higher power, you will see that there with this you will get a log u upon u square piece also at order G square, and with this 1 over u square at order G square. And plus if you try to analyze, there will be, you can see that log u whole square by u cube and all these things if you do a more higher order expansions in G and try to iterative your process. Okay.
Biswajit?
Yes.
So the R fall-off is 1 by R, right?
Right.
And when you say higher orders, so this is higher order is in U.
Higher orders in U. In a sense, R follow is fixed because we are computing only t hat of x mu nu, and this is independent of R. So R basically comes from the relation of E to T, or E tilde to T hat.
Right.
So this is fixed. So we are only looking at now the low frequency expansion or the last time expansion. So R follow is fixed. Now the U follows we are determining.
And this transverse traceless component. So if we write the metric in terms of Bondi metric, let's say. So then this transverse traceless component will correspond to the sphere metric.
Right.
Component.
Right.
So in that way, like the fall of behavior that can also be predicted from this scattering.
Right. So basically you can see that the CZZ piece, right? Because it will be 1 by R piece will cancel the R square 1 of the R, and this is linear in R piece, which is a CZZ. That should start with like theta of U to start with. And then there will be your 1 over u tail, and if there is omega to the power 0 piece, if you can construct, that will give a delta u, but that will not affect our memory because that only near u equal to 0 it will affect. After that it will not affect. So this doesn't contribute to memory. Plus this is order G. Then at order G square, so order G square you will have a log u upon u square plus 1 upon u plus some delta prime of u again, which will not contribute to your memory, and plus ... to try to analyze.
Right. And the graph that you have drawn showing the quasi-normal modes. So is it safe to say that the quasi-normal modes don't care much about the asymptotic boundary conditions, whereas the soft theorem?
Yeah, because quasi-normal modes with time it basically decays down, right? So it means it has a wavelength of order of the radius of the black hole, say. Right. And it if time increases, it is also 1 over R power. That I agree. But with time, that quasi-normal modes goes down. I mean, much faster than 1 over u. It goes like exponentially to the power minus u upon some Schwarzschild radius scale.
Yeah. So what I meant to say is that looking at the quasi-normal modes, the space-time, so whether that is asymptotically flat or not, probably that cannot be distinguished. Whereas looking at the soft theorem,
right,
that will carry a signature of what kind of space-time one is looking at.
So what I can say is near u equal to 0 or very small range of u equal to 0, that part could be affected by the quasi-normal mode. Because just suppose the gravitational peak passes and near this happens. But if you are looking at near psi plus, then it will not be affected.
1 by u behavior will always come from the soft theorem.
Right. Okay, so is there any other questions?
Biswajit?
Yes.
At the sub-leading order, is there a prediction?
Yeah. This is the order G square prediction what I have written here. This is the sub-leading.
Oh, but at order G, there's no sub-subleading.
No, at order G there is no, because once 1 by u, then it is delta u. So at order G, it turns out to be start with log u by u square.
Oh, okay. So at order G, the higher orders in U would be like proportional to U and not inverse of U.
Okay, no, it will, okay. I think the next, basically what happens is that in order G, it will come with G into omega to the power 0, right? Because starting with you have a 1 over omega, you have to multiply by G omega, so G into omega to the power 0. It turns out that G into omega to the power 0, it can be log of omega plus some constant. So for the log omega, it give 1 by u, the constant will give you a delta u, nothing else.
Okay.
Yeah, it stops here.
Achha.
And for G square order, you will have a 3 kind of terms, log u by u square, 1 over u, and delta prime of u. And if you try to analyze higher orders, there will be more and more terms will come. But what I can say is that only like if one try to do the analysis in the next order, only one can fix the leading non-analytic structure of order G square, not the rest of the piece, because those will depend on the region of R which you have chosen, like that this RL and RARB depends on those. And also the internal structure, if the black holes have spin or anything, then that would affect the 1 over u piece. And also if since the gravitational wave, those have spin, they will also taking out some radiation that will affect. So it is very hard to analyze the 1 over u piece, but one can analyze the log u by u square piece in a quite well fashion.
Okay. Just a comment to Manu's question. There can be other orders in U, meaning say at order G, the leading order is 1 by U, and then there's delta U. Then after that, there can be some higher orders in U, but those are very much non-universal. I mean, and
I think those. Yeah, I think there could not be.
Like in what sense is it non-universal here?
Meaning, depending on what kind of interactions you have, they will change.
Means that will depend on the inside the region or what is happening.
Right.
Okay. So naively, like it would depend on L or M on the Schwarzschild radius or something. Yeah.
Right. And the thing is that I think there will be no power of u. Like if you try to expand in power of u the other terms, that will not compatible with the G power. So it turns out that after delta u, the other powers don't exist, because if Gm omega is the dimensionless quantity, then this translates to the Gm upon u is the dimensionless quantity. Okay, and it turns out that if you keep the higher orders in u, then it will not compatible with the power of G, and from there you can say that it will stop only up 1 over u and delta u. After that, you will not get order G piece anything. Order G square you will have other. So you have to go.
Let me put it this way. So we knew that earlier there existed a subleading soft theorem, right?
Yeah, that is the delta u piece.
No, not the new subleading. I mean, delta u will correspond to omega to the power 0, but there was also an order omega subleading soft theorem earlier, which came from JJ, right?
Yeah, so that is delta prime u.
Delta, yeah, but at the tree level, so there was a contribution at coupling constant G.
Okay.
Yeah.
Okay, yeah. I agree. So probably, since delta u, delta prime u, and all these things are independent of, like, there is no u power explicit, so G power will not be affected by. Yeah. Exactly. So maybe with this here also there will be delta of u, delta prime of u.
Right.
All these
but those are very much non-universal. I mean, very much dependent.
Yeah, those are very much non-universal. I agree. And those will not affect the memory piece. Exactly. So yeah. Yes.
So I mean, not that I understand much here, but regarding this dimension counting argument, that Gm over U is dimensionless and other powers are dimensionful. Like if Manu was asking, like if some other scale comes in.
Right.
I mean, if there is some other scale, then you could make it dimensionless, right?
Right. So there is L is one of the scale. You can think the region size L, right? Yeah. And so that is other scale that will appear. But if you see that those kind of scale will not give any memory, like that will give delta u, delta prime u, if those kind of terms appear. So if you try to analyze in the subleading order G square, like one can see that those kind of terms appear, and those does not contribute to memory. So from the memory point of view, you can throw them out.
Okay.
Yeah. Now, with this so much calculations, I think I have only 2-3 minutes left. So let me give one example where we can apply this.
Biswajit, you started
Yes.
5 minutes late, so you can go 5 minutes beyond 12.
Okay, thank you. Then that will be fine. Yeah. Okay. So then let me give one example where we can realize how we can apply this formula from some astrophysical scattering process, and we can try to determine what will be the order of magnitude estimations of this tail memory and the DC gravitational memory piece. And we can say that can we, from studying this gravitational memory thing, can we infer some physics of these astrophysical scattering objects? Can we get some information beyond just testing that general relativity is true? Can we get something more about how the scattering is happening in more detail? So one of the example which I want to study is supernova explosion. So there is many kind of supernova, and I don't know actually what are the difference, but there is one kind of supernova called type 2b supernova, where basically what happens is that so one of the example is in 1987 people have observed one of the such kind of, I think type 2a, sorry. So one of the thing is that 1987 a supernova, where people have observed that basically one supernova explosion happens, and due to this explosion some neutron star kicks out. So and neutron star is basically in the same mass, in the same order of a black hole, or even the like solar mass order also. And one observes that the neutron star gets a huge velocity in this explosion. So from there it is clear that since along a particular direction one neutron star basically kicks out, so that must be asymmetric explosion. And so for this asymmetric explosion there must be some other particles which basically are exploding in the opposite direction to the neutron star to give a linear velocity to the neutron star from the momentum conservation. But these kind of objects people have not observed, only observed the neutron star. Then people have some model that which kind of objects are giving really the kicking, gives the kick velocity to the neutron star. And some people have some models tells us that like the neutron star, like the kick velocity is given by the core of the supernova explosion, which is some massive object. There are some models which tells us that there is some excess neutrino inside the core, and this excess neutrino gives the kick velocity to the neutron star. So, but still now there is no such kind of evidence that which of the model is correct, and both model up to now predicts almost all the observational data which people found. But what I want to say is that if you can observe this tail memory, one can differ that if the particles are some massive particles which are giving kick velocity, or the excess neutrino which are some massless particles gives the kick velocity. So you can differ between them observing this tail memory piece. So this is one of the prediction. Leaving that general relativity is true, this is already, I think, people from black hole merger problem and other things people already have better understanding. So for that, let me tell few things. That suppose to start with, you put a gravitational wave detector, the distance between the mirror is, so maybe I should not tell L again, I already used L, so let me put some, say D is the distance between the mirror before the scattering happens at u going to minus infinity, and at u equal to 0, say the scattering happens. The scattering means it is an explosion, so you can think of initially you have only one particle, so your m is 1, and outgoing particles you have some n number of particles, which is some 2 particles. One is neutron star, and other one is the ejecta particle, that could be massive or massless, and there is some gravitational radiation, which is a fine energy gravitational radiation, hard gravitational radiation. of finite energy. Okay, so you can study this process, and if you know the moment initial and find like okay, so what happens is that if you know the neutron star velocity and it turns out to be the velocity of this neutron star, say Vn turns out to be around 1000 kilometer per second. Okay, and from the mass loss, like basically most of the part of the supernova explosion happens spherically symmetrically, and one neutron star comes out and some ejecta material is there. So you can find out also what would be the mass of the ejecta material just from the mass energy conservation law, and the velocity of the ejecta material you can find out just from the linear momentum conservation, because you know the neutron mass and velocity that is observed. One finds out also like the ejecta material's velocity turns out to be some order 10 to the power 4 kilometer per second, and also mass are in order of the solar mass, neutron star mass. And also you can find out what will be the spherical symmetric part of the supernova explosion, what is the mass. This is around like happens to be very large, I think 10 to the power 5 solar mass order. And using all this data you can find out that what will be this, say, order of magnitude of the trace reverse piece of the metric fluctuation. So I am calling trace reverse piece only because like this will be the gauge, like if you remove all the gauge dependent component, this is the completely gauge invariant part, and this turns out to be like order 10 to the power minus 22 if you put all the data. So this is just order of magnitude estimation. Obviously this is some index are involved and all this thing. Now you know, like if you have this like detector position earlier D, and suppose you expect that the shift in the detector to be delta D, then you expect that the distance after this all scattering happens, this is the detector distance. Then you tell that okay, I have earlier metric eta mu nu, then the corrected metric say E mu nu, or maybe I should put ij. Delta ij plus Eij, and then where you put the detector distance between them, say di dj, and roughly then expanding this, what you will find that the delta d upon d turns out to be of order Eij piece, and that also turns out to be 10 to the power minus 22. Okay, so this basically tells us that the strain in the gravitational memory is also in the order of 10 to the power minus 22. And to evaluate this thing, the leading order also, like the leading gravitational memory turns out to be also 10 to the power minus 22, and the tail piece. And the tail piece, you have to depend on the time, obviously, so in which time you have to evaluate. So you see that the time what we are considering, the gravitational force is kind of weak. Only in that place we can apply our formula. So that means the kinetic energy, when just we can apply the formula when u is greater than some u0, where u0 could be determined in a sense, or we can tell corresponding to t greater than t0 because r is constant. So you can think that when the kinetic energy half of mv square should be potential energy of the particle. So this you can think of the ejecta, because the ejecta contributes the most, and m0 is the huge mass for the spherical part of the supernova explosion. And then you have this r is basically, you can think of v times t naught, and from there you can determine what will be the t naught is, and t naught turns out to be order of gm upon v cube. And with this t naught, after that you can use, so see your formula is valid starting from order t naught. So at t naught, if you just substitute, it turns out that the tail piece also have the same order 10 to the power minus 22. But what happens is that this tail piece is mostly gets contributed from the ejecta material, because this has a much more velocity than the neutron star. But what happens is that if the ejecta material is massless, then its contribution turns out to be 0, and only the neutron star contribution would be there. and it turns out that the gravitational tail part, memory part, will be much less than the part if the ejecta particle is massive. So the difference will be that if the ejecta particle is massive, you will get the same order of magnitude to the leading memory, which is the DC memory effect for the tail part at the time which I have told, and this for this process turns out to be some 1 second order after the explosion happens, if you just observe. So our formula will be valid after the explosion happens from 1 second onwards. And in that, if you have a ejecta material, it turns out to be that it will be order 10 to the minus 22, which is massive. If the ejecta material is massless neutrinos, the excess neutrino models, then it will turn out to be much less. Only the contribution will come from the neutron star long range interaction to the rest of the spherically symmetric explosion part. And observing these two effects, you can tell that the ejecta material is massive or massless. You can differ it. And obviously, just I want to make the comment that in LIGO you cannot observe this thing because the setup is such that this gravitational memory part they treat as a background. In a sense, there is some kind of pendulum system which basically keeps it swings it back to its original position in a time which is much smaller than 1 second. So one cannot observe this memory piece. But probably in LISA, which people are trying to put in space, so there one can observe this gravitational memory because there will not be any kind of pendulum system, and people can observe gravitational memory there, and probably there one can make sense of this. And the other example you can treat, say, for black hole merger problem, and surprisingly there what happens is that since for black hole merger you can start with the bound, like when the two black holes are rotating, this is a bounded object. So initial particle is one particle and final particle is again a single black hole and some hard gravitational radiation. And for that process, if you compute, it turns out that the tail piece 1 over u piece tail piece, I mean, if one compute the log u by u square, this tail piece of the gravitational memory vanishes. And this is surprising because the cancellation happens from the phase piece of the log omega and the long range gravitational force between the finite energy particles and cancels among themselves. But the origin of this thing is from two different regions. One is IR log and the other is UV log. So it is surprising that how this cancels, and we don't have kind of better understanding. But the prediction is that for black hole merger, the 1 over u and the log u by u square tail memory vanishes. So that's why I have not explained that thing detail, but this vanishes. And I think people need to understand this thing from some independent computations, why this vanishing happening. So I'll finish here if there is no question.
Okay, so first and foremost, let us all unmute ourselves and thank Biswajit for this wonderful series of lectures. So if people have questions, please go ahead.
Biswajit?
Yes.
So from the quantum side, you showed that the subleading log omega that can be written as S1 acting on the KGR.
Right.
Does something like this also happen at the subleading order?
Yeah, at the subleading order also, like I can write down the structure what will happen. So subleading order, you see, because there is a 2j piece in the higher dimensional soft theorem.
Yeah.
So the both of the j piece will operating on the KGR piece.
Achha, subsequently they will operate.
Yeah, subsequently, because if both of them operate on the KGR piece, then it will not contribute to log omega square, but the omega log omega piece. So that part you can throw.
Achha.
So if only each of the derivative operates on the k, then that will give each of the k has a log omega, so it will be log omega square, and already the subleading order has a omega piece, so omega log omega square order it will contribute. Mm-hmm. And in Fourier transform give log u by u square. And also there is a phase piece you have to multiply properly, that like the phase piece multiplied, like the phase factor also you have to square it and multiply to the leading, and the linear of the phase piece to the subleading order, those will also contribute to omega log omega square order.
Okay. Oh, so the phase
so
factor
you have to take care. Yeah, phase factor multiplied to the leading and subleading order also contributes.
Okay.
Yeah.
Any other questions? So if not, let us thank Biswajit once again for this series of lectures. So I will pause the recording now and people can continue the discussions in a more informal setting offline. Okay, welcome to the post-lunch session of day 5. We will resume with lectures on complexity in QFT by Aranya. Over to you, Aranya.
Okay, thank you. So in today's lecture, I plan to talk a bit more about Nielsen techniques and then move on to the circuit complexity techniques that was developed by Jefferson and Myers in their paper. So for that, so let's talk a little bit what we were talking about yesterday. So we want to basically, our goal would be to define a metric. Define a metric on SU2 to the power n for n qubits, and to do so, we want to generate a cost functional, which is sort of a, since the gamma function is a 4 to the power n minus 1 dimensional vector. F is a map from a 4 to the power n minus 1 going to some r, some real number, and we want to define a cost function which will be CF of gamma, which will depend on different choices of gamma, and among all of those choices of gamma, we want to get to the choice for which the CF would be minimum. And here, let me go back to the slide before here, or here rather. The sigma is the generalized Pauli matrices through which we write the time-dependent Hamiltonian, which we are going to sort of construct in a way which will depend upon this gamma t, and that will eventually give us the unitary that we are looking for. And so since this is in the circuit level, we write it in this form. And therefore, this would mean that these are exponentiated versions of this HT. And so these sigmas are the generators, or the Pauli matrices are the generators of the unitaries in SU2 to the power n, or generator of the group SU2 to the power n. So now let us decide that what properties we are going to desire for the cost functional. So the first property, because we want to eventually define a metric which should have these properties, we should ask for some reasonable properties which we want the metric to have. Therefore, we would want the f or cost functional to be smooth. Then positivity. So since we are, the complexity should give us some number in principle, or a sort of a measure where we count the number of gates. We want it to be positive. So the cost functional, for the cost function to be positive, we also want the cost functional to be positive. Definite, or it will be 0 only if, for example, the cost function will be 0 only if u equals to I. So since we don't consider identity gate in our universal gate set, so the complexity should give us 0 only if, and in that regime, say the gamma would be 0, or if y is 0 only if y. Okay, the third thing that we'll look for is positive homogeneity. And this is sort of related to realizing that we want such a, since we are dealing with the Hamiltonian here, a to the power I h dt. We want our cost function in such a way that if we double the intensity of the Hamiltonian, intensity is doubled, to get the same number of get the same cost or an invariant cost, we want the time to be halved. So we, instead of 0 to 1, we would take 0 to half. We want such cost functional as well. So what guarantees that is that we want alpha y goes to alpha f of y, where alpha belongs to any positive real number. Okay. And of course, y belongs to the 4 to the power n. So minus one dimensional vector space.
Can I ask something?
Yeah.
So since our gates are all unitary, is there how do you distinguish between whether I should call a gate the U or U dagger?
That you should predefine, sort of. You should, for example, this we will choose a few gates while dealing with the free QFT states. We would pre-decide over the gates what are the typical gates, those are sufficient to deal with. For example, in case of 2-qubit gates, we decided over that we are going to define the action in such a way that we will call the C0. How do you define the 2-qubit C0 gate? So we pre-decide over that. You could also take the dagger of that, but that would mean some other action that should also be equivalently available in the circuit. But the what we will see later also is that we don't really, since the unitary, for the unitary matrices, the daggers should also be equivalent to the inverses of those matrices. So we will not distinguish between whenever a U inverse is acting in the circuit, we would count it as U. So we would count that number, but as simply U. We would not include that gate as a different one in the universal gate set.
So there are target states where you have to act with the U dagger of the selected number of gates in your.
You don't really. There might be. There might as well.
So I don't know, but the reason I'm asking is it kind of felt like you're evolving backwards, right? Like if you think of the gates as an interval of some Hamiltonian evolution or something, then it feels like you're evolving backwards instead, and that sounds vaguely similar, like similar to maybe what do you say, some OT or something, right?
So similar to what?
If you say the inverse of a gate is like having.
Sorry, I can't hear you.
Okay, you were muted.
Yeah. Give me a second. I'm just replying to my parents here. Give me a second. 1 second. Yeah. Hi. Sorry. I'm so sorry for that. Yeah. So I thought like if you evolve, if a gate is like an interval of some unitary evolution, then the inverse gate should be like a back evolution, right? Or if you look at the relation you just wrote, if you think of putting a minus sign on it, I thought it's like, isn't it like, or am I reading too much into this?
I think you are taking the time evolution that we are modeling here too seriously. For example, it is not really, there might not be an actual Hamiltonian that could give rise to such a time evolution what we are modeling. But
no, but I could assign this, no? Like, do I use only the unitaries, or do I also have to use the unitary inverses? That is a sense of folding in time, no?
So I would say that since we are constructing the Hamiltonian through the by using basically the generators of the group, we are not using the gates by themselves, but we are using the sigmas, which are actually the generators of the group forming the SU2 to the power n. So sigmas, though themselves are not the universal gates. So sigmas can in principle also form any unitary in the space. So it can form the U as well as U dagger, and it
but
will
the
just
gammas
count.
are positive, right?
Yeah, gammas will just count, for example, whether at some point it is similar to, you can
no, there's
as an
some
analogy
positivity. There's a positivity constraint on gamma, right? Or
not
f of gamma, is it?
f of gamma, yeah.
Oh. Oh, okay.
I think it just counts the number of your universal gates being used, and gamma sort of gives you the, whenever you could, if you think like a binary action, you could think it of like at certain point of time, if certain gate is present, you tally one mark in the list where you are making where you are counting the number of such gates, and you would, for the inverse of certain universal gate, you would count that gate as not as the inverse, but at the same gate.
Okay. Okay, thank you.
Yeah. Okay. So the last property that we would talk about is the so we want if x plus y to be lesser than equal to fx plus fy, and we could ask why do we ask for this property, and we could argue that from a point of view which I'll talk about now. So if we fix a time t, and let's say we have our chosen or the optimal choice of control function, which is gamma. So this is the choice where the cost function is minimized, and now let us say that we there exist x and certain x and y for which such that gamma t at this time, okay, let's say this is t1, gamma t equals to t1, the gamma function behaves like x plus y, and we will also assume that for a very small amount of time, which we'll call, let's say, delta t1, this function, if gamma of s, let's say, let's call, or we could also call it t. So let's call it t. If gamma t doesn't change over the small period of time, and let's say we have another valid control function gamma 1, which is non-minimal choice. So we would assume that the cost function CF gamma is the minimal one, and for this we would call it to be gamma 1, and we assume that this gamma 1 behaves for any time 0 to
I don't know. There is a question in the chat.
Yes.
Whenever you are ready.
Yes.
Okay. So the question is from Lohit. He is asking what is this X? Is it number of gates used?
No, this is, for example, just a value that you would have at gamma is the cost function, right? And at a particular T1 value, you would have some value for gamma. Say gamma is a 4 to the power n minus 1 dimensional vector, and by x plus y, I mean the norm of the vector.
Does it answer your question? Okay. Okay. He says okay. Carry on.
So for the range 0 to T1, and again from T1 to rather T1 plus delta T1 to infinity, the gamma and gamma 1 are same. But gamma 1 has different property in the range T1 to T1 plus delta T1. Let's assume in this range, for example, for the range T1 to T1 plus delta T1 by 2, gamma is x, or rather 2x, and for T1 plus delta T1 by 2, starting from this time to T1 plus delta T1, gamma is 2y. So although this sort of violates the smoothness condition, but it can be regulated in a way that we can have another gamma function which is similar to gamma 1, but that gamma 1 equivalent to gamma 2, but is a regulated one and smooth. But this would one can show, although Nielsen hasn't shown in his paper, but he has said that it can be shown that the regulated one and the non-smooth one, the cost of these two can be shown to be the same. So if we take that statement to be valid, then what we can show is that let's say CF of gamma, we can say 0 to T1, we would have some F gamma dt, then T1 to T1 plus delta T1. In this range, as we have assumed, F gamma is constant. So we could simply multiply it with delta T1 as well. And again from T1 plus delta T1 to 1, you would have some changing delta function. So for this range, we have for this range and this range, the costs are same for CF gamma and CF gamma 1, as we have taken assumed that they behave in the same way for this range. But for this range, the F gamma is like f of x plus y, whereas the for CF, let me go to the next slide. For CF gamma 1, it would be, okay, I'm offline, I have to again. So for the 0 to 2 T1 and T1 to 1, For this range, they are same as CF gamma, but for the other ranges, T1 to delta T1, T1 plus delta T1 by 2, it is like f of 2x dt plus for this range, f of 2y dt. So now if we use the positive homogeneity property, we can write this part as again 2 of fx delta T1 plus 2 of delta T1 by 2. Actually, this part has delta T1 by 2 again, 2 of fy delta T1 by 2. So it would basically mean this part has fx plus fy delta T1 by 2. CF of gamma 1 has delta T1, simply delta T1, since this 2 and this 2 cancels. Whereas for in the same range, the gamma would have fx plus y delta T1. But now if we assume that since we have started this by what I started is saying, let's assume that I should have mentioned that this is not the case, and we actually have the other thing, that is fx plus y is greater than fx plus fy. Then this would be greater than this thing, and CF of gamma will be greater than CF of gamma 1. So this is a contradiction to our assumption that we started with, as gamma to be the gamma is not the minimal choice. Therefore, in this simple way, we can show that for a unique minimal gamma choice, we need the triangle inequality to hold. So what other properties do we desire the metric to have?
Can you go back to the slide? The one, previous one.
Okay.
Often go ahead and.
Yeah, I just wanted to see the proof again. That's it.
Yeah. Is it fine?
Yes.
Yeah. Okay. Then let's call our, say, new desired now be. So what would this mean? The say we have two unitaries and we want to call
sorry,
this as.
so just to be clear, so this f function is like the metric.
This is not yet the metric. Yet it is simply a cost functional, but we want the metric to have similar properties as this f function.
Okay.
And by again minimizing the metric functional and by taking a integration over metric functional, we would have some ds square type of term over minimization of which we should get the we should get a geodesic or geometric definition of geometric way of defining the state space or unitary space of SE2 to the power n. Okay, so let's say this is the metric, although I'll keep changing notations, but CUV is the metric which takes you from, and U and V are two unitaries. You want to, let's call it relative complexity. So CUV will similarly have greater than or equal to 0 property. Is 0 only if U equals to V. Then CUV would also satisfy the triangle inequality and so on. But what we want to also define is sort of we want this metric to be right invariant. I'm not going to go too much in details of right invariant matrix. That is a completely different thing to study, but I'll talk about at different points that why do we need this and such stuff. So we want the SU2 to the power n metric to be right invariant.
There's a question in the comments.
Okay.
Rohit is asking, is the function f anyway related to the distance function?
Of course, it is related to the distance function, or rather I should say it is related to the cost function in the notation that I have defined till now, but we want to define a similar length functional and metric which follows similar properties, where we would define the metric in terms of, say, some unitary and the control function.
Okay, so I have another question. I'm sorry. It's,
yes.
Regarding the previous proof that we did.
Yes.
So what we did is that we showed that if the triangle inequality is not satisfied,
yes,
then if I take a function f which is smooth,
yes,
I can sort of change the function arbitrarily and get smaller and smaller cost function. Is that what we mean?
The statement would be more like we would, for a very small time period, if we take another control function which behaves similarly for the most of the time, but for a very small time period it behaves a little differently, which can again be regularized to form some new, as I mentioned, some regularized one which is gamma 2, but which would have the same cost function as gamma 1. But then we can show that this gamma 1 will be the minimal choice of gamma, not gamma. So since we started with assuming that gamma is the minimal choice that we want to construct.
Yeah, but my question is that we assumed that the function that stays constant in that time duration delta t1,
yes,
is minimal. I mean,
yes, you could
that's
say
the only
that,
property we use, right? So
yes,
my question is that what tells us that? I mean, maybe we just found a different, function which is minimal.
I think that you could in any sort of define, if you have defined any control function, every control function is differently behave in a general sense, and you have two cost functions, or rather control functions, for which you for a time period you would have different behaviors. So a very small time period you ask them to have different behaviors. So one function doesn't change and one function changes twice, but it can be again regularized to something which is not which is smooth.
Yeah, maybe we can discuss this later.
Yeah. I'm also a bit confused about this part, so probably this would clear the confusion. So when I meant that although gamma 1 is not smooth, but we could regularize it in a way, Nielsen mentions this, that we could regularize in a way so that we could get to a smooth control function gamma 2, which will have the same cost as gamma 1. So we could also form a smooth gamma 2 function which would have a similar cost as gamma 1. So it's not about really being whether the control function being smooth or not.
No, that I understand. But my question is that we assume two things about the first gamma itself, right? We first assume that it's optimal.
Yeah.
And then we also assume that it doesn't change between this T1 to T1 plus delta T1.
Yes, but I think you could always assume that, for example, if you take a very small time scale, you could play with the time scale and see how the gamma function really varies with time, and you could always choose a very small time scale for which you could say that this doesn't change in this time period. You could keep, if it keeps changing for a good amount, then if you you could keep decreasing the amount of
So that was precisely my point. So the other gamma 2 is sort of at any minuscule time scale that I considered, it's sort of a varying function. It's not constant in any small time scale that I can consider.
Yes.
Right. So in that way, you have,
or
sort of
in
imposed.
that particular regime, these two gamma vary from each other.
Yeah.
Yes.
Hi, is the F like the action, or is F like an E raised to action, or is it not at all?
Yeah, I could think F to be similar to an action, but it would be clearer when we go to say the geometry which follows all these properties, and we could we have defined it from.
Yeah, but on action, you don't impose any positivity constraint, no? I'm just wondering, when we come to the holographic picture, then how does it act?
Sorry, can you repeat your question once?
We don't impose positivity constraints on action, right? But on f of x, there was a positivity constraint.
Yeah, that's because simply we want our positivity constraint to give us, since we are looking for a number or looking for a number of gates, we are just putting this constraint by saying that we want the number to be positive.
So how does this match with the holographic C equal to volume kind of things?
Okay, that is really, this is a qubit system, so you cannot really match from this perspective. But once I get to the Jefferson-Myers problem of defining the thing for free scalar QFTs, then at the end I will comment a little bit about this thing. So at this point, there is no way to realize this thing.
So just to anticipate, like we would do away with the positivity constraint on F.
Sorry, the last part I could.
So for the field theory, would we do away with this positivity constraint, or?
No. We would still assume that the number we get is a positive number, since we are trying to you cannot have a negative gate or something like negative measure of circuit complexity.
So then F is more like a e raised to s, is it? Maybe Euclidean e raised to s.
Okay, I'm not sure.
Okay.
Yeah.
Hello.
Yeah.
For the proof, I think, I mean, if you, can you go to the previous slide?
Sorry?
Can you go to the, previous slide?
Yes.
Even before that.
Okay.
I think if you can prove that the smooth function, and if you take this gamma 2 as the argument and gamma 1 as the argument, and if you subtract both of them, if the difference is order delta t1 square, then I don't think there will be a problem.
There will be a
no, I don't think there will be no. I mean, if you can prove that gamma 2, CF of gamma 2 minus CF of gamma 1 is of order delta t1 square. Then,
but with the assumption that we had, we did have fx plus y greater than fx plus fy, and we run into a contradiction due to which we choose, say, maybe we say it sort of a reason to choose fx plus fy is less than equal to. So in this case, what you're saying is CF of gamma minus CF of gamma 2 is less than some delta t1 square order.
Yeah, I mean CF gamma 1 minus CF gamma 2.
Okay. So in that region, what are you saying?
I'm saying that if you can prove this statement, then I think the proof will go through. I mean, without any ambiguity. I think so.
Okay. Maybe that is related to the way you regularize the gamma 1 to gamma 2. Yeah. Okay. So by right invariant metric, this is actually, I'm talking this roughly because this tells you about mostly, this is something called unitary complexity, but what I will be talking about later is state complexity. So we are, there we are going to use unitaries in and we model the states by the states themselves. We don't model the states by the unitaries, but as a just as a motivation to realize how it could be how the right invariant metric could be motivated, I would use this thing for a while. So let me say we have two unitaries from which and we use say C number of gates in here to get to U from V. And now right invariant metric means if you multiply for this you have certain C of UV. If you multiply some W in right, this will go through and it will also have in here. So this will be equal to C of UW and VW. But if you sort of say, why isn't it left invariant? If we had multiplied the same W in the left hand side, then if we call this whole set to be GC, then it would be WGCV. We could write it as WV. But for again these two complexity to be same as CUV, we would need this to be same as GC, or the count should be same as GC. But there's no guarantee that this should lie in the same space of n qubit gates. This is sort of a way to motivate for this, but this will be clearer when we actually deal with the field theory or harmonic oscillator scenario. I'll talk about these things more or point out where the right invariance is.
Sorry, why would it not lie in the space of n qubit gates? Because all these are unitary matrices on their own. If you multiply them, you get a unitary matrix, right?
Yes, but it might not be the same. The W's and GC's are not the same unitaries. Your W can be any arbitrary unitary, and this could not be in the say set of allowed universal qubit gates.
Okay, that I agree. Yeah. Okay. Yeah. Okay.
Okay. So just after doing this, so just as a point, I would like to mention that this metric that we want to have is very much different from inner product metric. For example, if you would have say, let's say upspin is characterized by 0 and downspin is characterized by 1, then you have 3 upspins and 1 downspin state, a 4 qubit state, and you want to get to a state where all the spins are upspin. In that case, these are sort of orthogonal states in the 4 qubits, orthogonal states in the inner product space. So the inner product would give us 0. So in inner product space, they are like maximally distant, which is the pi by 2. But in the complexity space, you could simply act by a gate which would transfer the 1 to 0, and the complexity will simply be 1. in this case. So this is the complexity is very less for this case. So this is an example where you can see that inner product, this is small, and this is maximum distance one can have in an inner product space. So they are very different from each other. Now, let's talk about the metric that we were talking about previously. So the properties I mentioned beforehand, all those properties are satisfied by something called Finsler geometry, where you say you'd write some d of, let's say, some c as
Aranya?
Yeah.
I'm a bit confused because it seems like we are switching between like state complexity and unitary gates complexity. So like, I don't know about this much, like, are they related? And
so
because earlier we just had this U and V, both of which were like unitary, but here
yes,
we have these states, which are like states in the Hilbert space. So I don't see the connection between that metric and
so you could, in principle, if you are talking about the basic notions or the basic ideas that you want to have, they will be, and people have sort of also shown that state complexity or gate complexity, they are in some cases up to a normalization constant, they are same. So the behavior in general should be same, invariant of whether you are dealing with distance between states or you are dealing with distance between unitaries.
In state complexity, you have this initial state, right?
Mm-hmm. Yes.
And the complexity would depend on like which initial state you choose.
Yes.
Whereas here it just seems like distance between two unitary operators.
No.
So where did that go?
Okay, let me put it in this way. So we had written two things, U of Shaya, and we had also written as power minus 0 to 1 HT Shaya. So if you take these two to be equivalent, you want to basically, although you have a reference state, you have a target state, this unitary which you want to specify, let's say this should be made of certain many things this side, and I will call this part as, say, US as some exponential
okay, I guess the gammas in the Hamiltonian will contain the information about these initial
unitary
and final states.
Yes, of course.
Okay.
And those gammas using this formalism, if you want to, then using this you could show that, for example, here I was writing this US, which is this U exponential over HS. Let's say I denote the time coordinate as X, and I have this one, which, okay. Let's write it in this way, where I have absorbed the minus I sign in here, and this is so this are like minus I sigma is an anti-Hermitian, and yi of S's are the control functions gammas of our previous system, from which you can actually show that there will be no exponential inside this, but that will be outside. From this you could show that the del U del S would be related to, could be related to something like YS mi time us, if I'm just let me see what's the exact expression.
Okay. This is what you had yesterday.
Yes. So here you could, in principle, this u dot s, you could also all the time dependence of this u dot s, you could write it in terms of the ys. And then what would you argue for is that so in the Finsler geometry, this is a more general class of geometry than the Riemannian geometry, but it
Can
includes...
you just copy paste that equation, because
yes, I will write it again once in a...
okay, great. Thanks. Yeah.
Okay. So for the Finsler geometry, all of the previously mentioned properties satisfied, and we could write a measure of distance in this geometry by like this, where f of ut u dot of t. So this is sort of also saying we need to know a position and momentum of a particle to get hold of the trajectory or some positions in momentums. So the idea is to then, there are some choices of this cost functional for which Nielsen mentions that there are lower bounds on the number of gates. And this at this part we'll shift to the Jefferson-Myers paper, where we will discuss in details. Again, we will, as Subbu was going to ask, we will actually come back in more details what we actually mean here. But there are some choices of f. We haven't yet mentioned the choices of f's for which the lower bound of on the number of gates are there. But let's take it from here and go to the problem we actually want to deal with. So the choices would be, to be precise, and let me mention this. As I mentioned, all of these properties are satisfied. They are satisfied in the Finsler geometry. They are, by definition, they are supposed to be followed by this second functional, or the, let's call this v. So the triangle inequality, positivity constraint, all of those things will be followed when we are writing f of gamma. The gamma would be this ut, as I was mentioning to Subbu, this will be equivalent to yi. So this would be equivalent to the gamma, and whatever properties that we asked for the f gamma thing, that would be in terms of the second entry in here. So what are the choices of cost functionals that satisfy the lower bound? And in the Jefferson-Myers problem, we will also choose one of them to be the case. So yi, for all yi's, if we take this is one choice.
Can I ask something quick?
Yes.
Yeah. So in your previous slide about this is also related to what Subbu asked.
Yes.
So so these yeah, I'm wondering what this u is. So do you mean that these gamma that sit in the Hamiltonian with the gamma into sigma polymatrices? So do you mean that you always assume to begin with in your state to be in one of the generalized polymetrics, and then on that we apply the gamma matrices, and those gammas are the unitaries u that you have written above? Is that
no? So the Pauli matrices are the generators of the elements of SU2 to the power n, and so the Pauli matrices are generators of these unitaries as well. And since it was exponentiated in the to the power IHT form as well, and H had this gamma and Pauli matrices, so
yeah,
they were sort of generating the gates, and by optimizing the Hamiltonian, we are counting the minimal, we want to count the minimal number of gates, but okay. Let me just.
But if you have to optimize gamma, you have to choose some initial state, right? Otherwise, how would you?
Yes. That's what I will talk about during this circuit complexity business.
Okay.
But Subbu, can you comment on this thing about the difference? I mean, this switch over between the we are now talking about a metric which takes us from a unitary U to unitary V, but we were earlier talking about the transition from one initial to final state. Yeah, I'm also
actually we are yet talking about the state complexity. We are going from a state to another state, but we want to represent the unitary which takes from one state to another in terms of the optimized Hamiltonian, where the input of this. Yeah.
I think if the initial state is fixed, like they are equivalent. Like.
Okay. Yeah, I see. Yeah. Thanks.
What is D here?
So D here would be similar to what we had in general C of f of gamma, but you have to minimize this, take over all choices of f, or for a single choice you have to consider in this geometry the geodesic from going to compute the geodesic length, and that would give you the minimal of this thing. This is sort of a, if you ds or ds square kind of a thing. So minimum of this thing, this is typically called circuit depth, and minimal of this thing would give you the circuit complexity. Okay. So there are other choices of cost functions as well, cost functionals, which are, this is not a power. And in here, I'd say that, let me back. Similarly, we could have these are the 4 cost functionals that Nielsen talks about in his paper, and you can see that Riemannian geometry would come out of this cost functional. This looks similar to what we deal with in, say, had we taken GIG.
I don't know.
Yeah.
I'm extremely sorry, sir. I'm feeling a little lost here. So, why are you going even to Finsler geometry? What's the reason to go to Finsler geometry? You have defined a cost function and all. Now, why do I have to go?
Because I want to reduce the problem of choosing this infimum from getting to a particular choice of minimized complexity. I want to be more specific about this, and that's why I want to geometrize the problem in a way so that the problem of choosing this minimum goes to choosing a geodesic path between the unitaries. So I want to define a manifold on which the unitaries live, and I want to calculate the distance between, minimal distance between them.
Okay, then why particular this Finsler geometry? Why not Riemannian? I mean,
so
Riemannian, that this is not Riemannian geometry. This is more general than Riemannian geometry, right?
Yeah, this Riemannian geometry, for example, this would be similar to Riemannian geometry, this cost functional choice. And you would also say, for example, Finsler geometry is chosen because it satisfies all the property that we desired from the F gamma, for the F gamma cost functional. You can always choose, you can be more specific and choose Riemannian geometry, but ideally you should choose the broader class of general geometries that follow all the desired properties of the F gamma.
Okay.
So the right invariance, we could also write it in this way. So we could talk about it in this way, that HT is the sum of rather YIMI, and this would be path ordered, by which I mean that the earlier time operators are acted first on the, so when you acts on psi t, the it starts from that if I instead of time, if I think this about some affine parameter on the space of unitaries, then this would simply mean the for lower values of u or lower values of s t, those operators will 0. Let's some operator, some unitary of at 0.5 acts before some unitary, and so we build the circuit right to left. We use the earlier time operator first and later time operator in the left hand side, because those will only give me the non-trivial things. Had we multiplied this in the right hand side, this could mean this would be equivalent to something else, since we are also dealing with unitaries in here. And we what we wish is that at t equals to 0, this would be identity. So at t equals to 0, you would still have psi reference, and at u at t equals to 1, we reach the u target state, or if we call this to be the u target. Okay, so finally, let us with this choice, let us get into the complexity of free scalar field theory. And all of the things that I have been talking about will be, I hope, clear in this part, where I will be definitely talking about the states and how do we quantify the states, or how do we understand the states, everything. So we'll deal with let's deal with this Hamiltonian. Which is a Hamiltonian of a free scalar field theory in d space-time dimensions. And we regulate it by introducing it on a lattice, where the lattice spacing is delta. Then the Hamiltonian looks like this. It is relatively easy to get from this and this, and maybe when I'm writing the notes, I could derive this thing as well. You have to just put in some information and you would get this form. Where these xi's are unit vectors pointing along spatial directions in the nearest neighbor point. The lattice. Okay, so with a few definitions of variables.
Can you go back to the previous slide?
Yes.
Okay, thank you.
Yes. Okay, so with a few redefinitions, we could also write this Hamiltonian in the following form. So this is simply a problem of, so this runs from some n to n to the power d minus 1 over 2. Problem of dealing with huge number of coupled harmonic oscillators. So introducing this on a lattice gets reduce the problem to a problem of huge number of coupled harmonic oscillators. And for the warm-up, as a warm-up problem, we'll start only by dealing with two simple harmonic oscillators or coupled, which are coupled to each other. And let us write by taking these m's to be 1, the masses to be 1, we could write the Hamiltonian for a two oscillator case in the following form. So x1 and x2 are the spatial positions, and p1 and p2 are the canonical conjugate momentas. Okay. And if we go to normal modes, where the normal mode positions would be defined like this. Then we would simply be able to write this Hamiltonian as a decoupled version would be square, where this omega plus square is related to the coupled scenario here, this omega square, and omega minus square would be simply omega square plus 2 omega capital omega. So for the decoupled versions, we know that the wave function of two decoupled normal mode oscillators can be written as a multiplication of each of them. And this should be simply this thing. Now, if we go back to the coupled parameters, that is omega and capital omega, then we could write this actually would be in terms of x1, x2, the actual position basis. Actually, we are not going back to these parameters, but we are going back to the position basis thing.
Aranya?
This, yeah.
Your second line, you meant to write psi 0 of
Yeah,
x
yeah, yeah.
plus
Sorry.
times.
Yeah. Yeah, thank you. Minus a coupled term will be there in the wave function as well. And here so what I mean to say is here you will get a x1 x2 term in the exponentiated part, and so here the omega 1s, let me clarify what I mean by omega 1 and omega 2. They are simply the defined as this omega 1 plus omega minus. We defined this omega 1 and omega 2 be omega 2 to be different here because we want to talk about more general class of states where omega 1 and omega 2 might not be the same. Okay. And beta is okay. So this state, let's call this state to be our target state, and this wave function we want to reach to this wave function where there is a coupled term. Now while talking about this, I should be more specific, like while defining the states, primarily we will only define them in the physical basis or in the physical position basis, not in the normal mode basis, because in the normal mode you would still find there are no coupled terms, and typically one chooses the reference state. If I call this the target state, one chooses the reference states in such a way in which that it's a state where in the position basis also there are no coupled terms, there are no couplings between x1 and x2 in the exponentiated part of the wave function. So that is how by what I mean entanglement in here is in the physical position basis. There will be no entanglement if you go to the normal mode basis. And so we
I don't know.
There's a question in the chat box. Shubham is asking, sorry, I missed. How did the SIT came about? Shubham, you can ask him directly.
Yeah, I meant that SIT is the solution for the interacting Hamiltonian. You're assuming that or something?
So no. Interacting Hamiltonian because, or we could say that this has coupling in it.
But
so
it can be anything, right? I mean, I could have
be anything. Yeah.
Oh,
this is not any general. This is just a generic one. This is not something very particular one.
I see. Sorry. Yeah.
Okay, and we'll call our psi r, as I was talking about, that we typically take this to be unentangled state in the physical position basis. So there will be no coupled terms, and you would simply have, let's say, omega 0 over 2 x1 square plus x2 square. And this would be the reference state, and the target state would have something, again a normalization, with which we would have both x1 square terms, x2 square terms, and x1 x2 term. So now let's talk about this is a very particular choice of gates that we'll take here. One could also take other choices of gates. But we would stick to this one, and we would choose a number of gates which sort of are enough to produce this state from this state. So since we don't have a very clear notion about what should be the universal set of gates in this case, we start from a basic principle. And so the gates we will use should be related to anything that is all we have here and should be acted on by as an operator, or should be functions of x1, x2, p1, and p2. Let's say we take a few gates. H is one gate, which you define it as x0 p0 to the power I epsilon. Epsilon is an infinitesimal number. Then JA specify this x0 PA, K specify this epsilon XA P0, QAB where A not equal to B is e to the power I epsilon XAPB, and finally QAA is e to the power I epsilon over 2. This part is also in the exponential.
So why did you take psi-t to be this? This is the ground state, right?
Yeah, I'm still talking about ground state, but the degree of entanglements are different. So when I say that, I should be saying that in circuit complexity, all the differences that have been calculated till now are mostly the complexity between different ground states. There hasn't been a concrete calculation where you really compute the complexity for excited state.
Okay.
But in the ground state itself, in the physical basis, you have in one case you have entanglement, or the things are coupled, but the reference state, in case of the reference state, they are not. So let's see what these different gates does to our wave function.
There's a question.
Yes.
Yeah, Aranya, how do you know that these gates are simple enough? I mean,
I'll just say that how these operate on a system, and the basic things that we need the gate to be doing, whether they are able to do so or not.
I see. I mean, just to anticipate, like, would we see anything like it will act only at two sites at a time or something like that, or would it be more non-trivial?
For example, here we per se we have two sites at most, because we are dealing with two harmonic oscillators, right? And
so here we anyway
be,
have. Okay,
yeah. So here we will be we will see in which case there is which operator introduces some entanglement or couples these things in the exponentiated part, and in which case it is like just a scaling.
Okay.
So H operator.
Lata, go ahead.
Yeah.
Yeah. So can you also see them as the universal gates we discussed for 2 qubits?
Yeah, we will discuss more about these things when we talk about actual generators of this algebra and how do we specify the generators and everything. But this could be roughly, there is no way to guarantee that these are the universal set of gates. You could have taken other powers of x's and p's in your exponentiated part. But for the problem at hand, that is going to this target state from this reference state, these set of gates are enough, sufficient.
Yeah, because I asked because this looks like a quantum operation from the point of view of algebra, but I was wondering if it can actually be recasted into the unitaries we talked previously.
Yeah. Even, but it is going to be different from the unitaries that we talked about. It was for the n qubit case, whereas we are dealing with harmonic oscillators. So here, to for example, to specify a state, you need like a 2x2 for these two oscillator system. You would need a 2x2 real symmetric matrix, where the elements should be simply omega1, omega2, minus beta over 2 and minus beta over 2. In case of the target state, this is the matrix, whereas for the reference state, it would be simply omega0 over 2, omega0 over 2 diagonal matrix, or the unentangled reference state.
Yeah, okay, thanks.
Yeah. So the H operator, which I defined in the previous slide, which is this one, x0 to the power I epsilon x0 p0. It's simply acting on psi x1, x2, where x1 and x2 are the positions. It simply changes the phase, global phase change, It doesn't do anything else.
Aranya, sorry, I might have missed it. Can you remind me what is X0 and P0?
X0 and P0 are like sorry, what did I say? X0 and P0 are the like time coordinates, and del T, you could say.
Like we have X1 and X2, right? Like two particles.
They are the
on
position
2 sides.
basis. Yeah.
Okay. And X0 and P0 are what?
For example, in your 4 momentum, the things you have as time and del T, time operator and del T, usually. X0 is your T.
Okay. Okay.
Yeah.
But usually when we write T, we mean, I see. Okay, X0 is T. What is P0?
It's similar to, for example, the momentum in P1 is like we call it del X1. It is, you could call it to be del T.
Oh, I see. Okay.
Yeah. Okay. Then this
No,
is a
sorry, I still with what Subbu asked. Just go back one slide. I still have a confusion.
Yes.
So X1, X2, P1, P2. So X1 is the position for the first oscillator kind of thing, right?
Yes.
P1.
Yes.
Then X1 is itself a 4-component vector. Right?
No, here by position we mean only the actual position.
Okay,
Here,
and then X0. So that means X0 is a time, like a common time or something like that. It's X0.
they are the common time for X1 and X2. Yes.
Oh, okay.
Yeah. Okay. Then K1, what it does is, let us look at K1. What it was, K1 would be e to the power I epsilon X1 P0. So what it does is simply shift P1 or the momentum of X1 as I epsilon, or what should I say, not X, epsilon P0. Okay, then Q21 is the operator here. Q21 would be to the power I epsilon X2 P1, acting on psi X1 X2. So P1 is the generator of translation, and so it changes the position of X1 from this to X2. And this is so this is called an entangling gate. Depending upon what X2 is, it will change the position of X1 that much. So Q1 will be Q12 will similarly be changing it to some X1 to X2 plus epsilon X1. And what Q11 or Q22 does when these are the cases, to the power I epsilon over 2 XAPA plus PAXA. That simply introduces scaling. So this we will call the scaling gate. So there are by K2 we would have realized the shift in P2. We have entangling gates, we have a global phase change, and we have a scaling gate as well. So these would be the basic ingredients that we will take in here. And say, let's talk about a few
Can
circuits.
you go back?
Yeah.
What does J do?
Oh, sorry, I forgot to hear. So it would simply shift the position by a constant shift. It will be like a not an entanglement, but just a translation. Here, by e to the power I epsilon P0x1, the momentum was shifted. And when you introduce, say, J1, so x1, it will just shift the, okay, my iPad has gone offline again.
Aranya, I had a question.
Yeah.
Yeah, this shift, is it happening on the lattice that you described?
Not yet on the lattice, but we are, since I mentioned that we are now warming up with the only 2 lattice points or 2 oscillators case. So in that space, the oscillators are moving only.
The lattice, so the 2 lattice is it like a ring or is it like a line?
Is it? It is, for now, it is just a line. It is just 2, in a line, 2 things are attached to each other. 2 oscillators, I don't know what would, oh, so you are saying whether they are connected from both sides or not?
Because if you want to shift it, then, I mean, if it is in a ring, then you are moving back to the same points, right?
Yeah, it's not in a ring. It's a simple situation where we have 2 points and it's connected by a single spring.
Okay.
Okay. So there are a few exercises that you can do with these things, which are easily doable. Say, for example, we want to know what would be the circuit in here, going from the reference state to target state using the set of gates that I mentioned. And you could do that by, let's say, we choose a particular way of doing it. We don't know anyhow that whether this is going to be the optimal one or not. So this should act first, then this should act. And so there is 1 entangling gate and 2, let's say, what is this? Scaling gates. So the job at hand would be to go from like omega 0, omega 0, 0, 0 to omega 1, omega 2 minus beta over 2 minus beta over 2. So I need to scale these things as well as introduce off diagonal terms, which will be introduced by the entangling operators. Which if we do this, we could, by solving different parameters, we could find alpha 1, alpha 2, and alpha 3. For this choice of gates in this ordering, you would find that alpha 1 would be it is very easily doable. You could simply multiply these things and see the change in exponentiated part, and you would want to get to omega 1 from omega 0, then omega 2 from omega 0, and then so on. Alpha 2 would also have some value like omega 1 over 2 alpha.
Alphas are what you would put instead of epsilon in the Qs,
no,
right?
here these alphas are sort of giving me the numbers of gates used. So let's say this is very much a rough scenario. I don't know whether this is anyhow going to be, this is not going to be itself the minimal condition, but just a way of writing how we want to calculate the things. So let's say we are using alpha number of Q11 gate, alpha 2 number of Q21 gates, and alpha 3 number of Q22 gates. Then what would be the alpha 1, alpha 2, and alpha 3 that would correctly reproduce the target state from the reference state?
Okay.
Aranya, I have a question. Sorry.
Yeah.
Okay. Yeah, I have a question. Like, I mean, alpha 1 and alpha 2 need not necessarily be integers, right? I mean, or is it always guaranteed to be integer?
No. It need not be integers. Yeah.
But then, I mean, then what does the operation mean? Like, I mean, you are operating and some operator, some fraction.
It would also mean, because we have taken this e to the power I epsilon or an infinitesimal operation, we are dealing it as some infinitesimal operation only. So on choosing different epsilons, you could maybe vary alpha 1 as well, and if you could get to some integer number. But otherwise, they are just, since epsilon is kept arbitrary, they would ideally be some positive real number.
For small enough epsilon, I mean, all of them will be integers, right?
Yeah, you could think of them as integers, but they would be represented, for example, like this. Alpha 1 is like 1 over 2 epsilon log omega 1 over omega 0. So there is no guarantee that you would get this to be an integer.
Yeah, that's what I'm saying.
Yeah, but if we make like epsilon small enough,
yeah,
then we can think of them as actual processes with integer number of steps, because whatever is the fraction, like we can suitably adjust epsilon.
Yes, that's what I was saying. So since we have the arbitrariness of epsilon also there, we could always use that to modify.
I have a question.
Yes. Sure.
So just to be clear, you are not saying like that this form is the minimal form, right? Like for example,
no, in no way.
No, yeah, like just to make it clear that, for example, it's not even necessary that all the Q2 should act together. Like they could be sandwiched in between the other two as well.
Yes,
right?
yes.
Okay.
And in fact, if you just change the way I have written, say you use different ordering, alpha 1 and Q21. Q21 is acted first, then if you act by Q11, and then if you act by Q22. That is a simple way of realizing what Subbu was saying. We even don't change the this power, but we simply change the positions of these two. So even then you will see that this alpha 1, alpha 2 and alpha 3 values, they will change from what they were earlier.
Also, I meant even all the Q21s need not even be successive.
Yes, that's also the case. So,
Aranya, just to tell you that you have 3 minutes remaining for your usual time, and we'll give you 5 minutes extra.
Okay. Okay, so now what we want to do is basically choose, what should I call it? Okay, let me write it in this way. So by U should be written as mod of alpha 1 plus mod of alpha 2 plus mod of alpha 3, or in this simplest setting. It is not going to be the case in the most general setting, but in the simplest setting, it is going to be like that. And you have to take, whenever there can be situations where alpha 2 comes out to be a negative number, but you have to take the mod of that, because the negative number can also be due to actually the inverse is used. That might also result in a negative number. So since we take the inverse and the actual gate to be the same gate, then therefore we use this mod function. And okay, so the final, or the way we want to actually go in the business of doing this is by writing the actual things, where this analogs of this alpha 1, alpha 2 and alpha 3 would be the YISS.
So you're saying we want TU, final answer of TU should be alpha 1 plus alpha 2 plus alpha 3, and we should find out how to get that from
the one way of saying this, that how many numbers of alpha 1, alpha 2 or those Q11 or Q22 gates were present. They are sort of saying that at one point of time, what was the control function. We will know exactly what the control function is later, but this is similar to saying what is the control function, and therefore I want to basically calculate, this should be a different one. We want to say calculate this cost, and we will see how this cost actually we can write in terms of some the MIs or the generators of the group and similar things. So let's stop at this point, and we can go on in the next lecture talking about other things.
Okay.
How do we exactly talk about the YIs, MIs, and how do we calculate the complexity for two oscillators, and what intuition that we get from the calculations for the N oscillators.
Okay, so first let us thank Aranya for this lecture. Rohit, you can go ahead and ask your question.
Yeah, so if you could go back to slide number 28 or 27. Yeah,
yes.
So the state that you have started, like 0001 goes to
yes.
000. It can be achieved in many ways. Like you can start from 1 tensor dot 1 tensor dot 1, then x, and then it flips. 1 goes to 0. That is one way of achieving. And then there can be other many complex ways of achieving that also.
Yes.
How do you incorporate the information about the system in the gamma functions that you are using? Because that has to be incorporated. Otherwise, if you do not have any kind of constraint like that, then you can just start from any state and go to any state, and the least possible state would be the least complex one, irrespective of the system that you are choosing.
So you mean if I'm not talking about the minimal version of this, then what would, how does gamma knows about the other possible paths?
Yeah, so my question is like, so it's a four qubit system.
Yes.
I can have any 4 qubit system which represents the 0001 thing, and then I can do some modifications, and then I can go to that all spin up case. Now, how does gamma contain the information about the system itself, that 4 qubit system that it is not any random 4 qubit system, it is this particular 4 qubit system or that particular 4 qubit system? I don't know whether you are getting my point or not.
But the way you want to define gamma is also dependent on your final state and your reference state, right?
Yeah, but the same final state and reference state can be produced in n number of ways.
Yes.
So how do I know that one particular way is my way and I'm trying to look the optimum? Say you are looking at 4 random spins, and then there is just some magnetic operation at the end of it. You want to see where all those spins are lined up in particular way or not. So you do some detection, and there are some gate operations, say, through those detections. So there is one thing that we want to just look at that particular system, and we are computing available gates and minimizing the number of gates to solve that particular problem. But there is one thing that given any criteria like that, irrespective of whatever system it is in, and I get the same kind of final state.
You get the same kind of final state. I don't see the point. If you have some reference state and you have some target state, you have infinitely possible choices of gammas that you could use to go there, which will be basically the different combinations that you could have for reaching one state from another. Now in the space of the gates, you want to realize it as a manifold, a Finsler manifold, where you define geometry in terms of those gamma functions and those control functions and the generators of the unitary group, and you want to construct a metric. Now the finding the minimal geodesic between the 2 points that you are interested in, there can be actually, in the case of 2 oscillators, harmonic oscillators itself, there will be a 1 parameter family of geodesics, and you have one has to find the minimal one among the minimal length geodesics among all of them, which guarantees that this is the minimal path among all other choices of gammas. And you write the matrix, using the information about or the representation of the control functions. You construct the matrix, keeping it in a general shape.
Okay.
Okay, we have 2 more questions. Shubham, go ahead.
Yeah, so can you just go back to the example that you were working out? And I have just some basic doubts about Psi T.
Yes.
I did not understand fully like how you chose that. Like, I mean, so say for example, can you go to the place? Yeah. So here, could I have chosen like beta x1 square plus x2 square? Something
x1
like
square plus x2 square. I mean, but which one in the target state?
Yeah. Like I mean,
yeah. You could choose, and there are no x1, x2 terms.
No.
Nothing. You could choose any of any 2x2 real matrix of this scenario, and the formalism that we will build will basically keep track of the states as these 2x2 real symmetric matrices. So you could have any element in there. I have just considered these 2 as an example.
Okay, Subbu, go ahead. Subbu, are you there? Okay, so maybe temporarily we have lost Subbu, but
Hi, I'm here.
Yeah, go ahead.
Okay, so what I wanted to ask is, you took your reference state to be the free ground state, right?
Yes.
And the target state to be the interacting ground state,
Yes.
right? And now, I mean, okay, firstly, how do I say this? So if we actually do a physical process, I mean, if there is an actual physical process where we begin with the free ground state and then the interaction is turned on, then the evolution will happen with the actual physical Hamiltonian, right, of the system.
Yes.
So now what we are doing is we are considering these states as some vectors in the Hilbert space.
Yes.
And we are taking some set of gates that we are defining as elementary gates. Okay.
Yes.
And then we are computing the number of them. It is not clear to me whether from the physics point of view, I mean, I don't want to go into the later details, like in holography, it might be important. It is not clear to me, like just from, like, let's say 2 coupled harmonic oscillators, if this number is of any physical importance, if these set of gates are of any physical importance.
No, these are not of any physical interest. You could also have the idea is to, for example, when in the next lecture, we will basically see that for a 2 oscillator case, this is we represent the state by a 2x2 real matrix, and the state of unitaries, the space of unitaries will be basically GL2, R. So basically it will be any general linear 2-dimensional real matrix. So, and all of them can be, since all of these H, J, A, K, Q, A, B, all of these would be in that general class of possible linear real matrices. So we include all possible matrices in there, where we actually work with the generators to be the generators of GL2, R group.
Okay, Pawan, go ahead.
So I'm still confused. What is gamma, Y, and U? You have in some places gamma and some places Y.
Well, that was just a change of notation. I sort of you could take the gammas to be the same as Y's. Just I changed the notation somewhere where I introduced this included this minus I inside the sigmas.
What is U and U dot?
U is the unitary that I represented that takes, for example, you could think of it as any possible. Let me write it in this way that might make it a bit clear. So if you write U of S, unitary that takes you to the final state from the reference state as a general unitary, I have not yet defined the 0 to 1 condition. I am taking it to be 0 to S, and I am integrating over some other exponential will be also outside the mi, and this yi's will be function of this thing. Now, for the particular circuit I am looking at will be at U0 is I and ut is equal to 1 at the unitary that I want to reach. Now, you could take from this expression, what you could write, just working a little bit on it, is yis mi. You could have written that as del u of us, where u is a s-dependent operator, kept as a s-dependence. You could write it in this way. So if you take del us of this expression, you would simply get a u into the same thing with these parts coming outside the exponential, just like when you take a usual derivative. And therefore you could also write the yi's sort of this way. When you go to the matrix representation of these generators, you could choose the trace of mi transpose to be 1, and then you could simply take the inverse in this side. Then one would write yi would be del s u inverse of mi. Now it's sort of when you write this expression and add us and yi mi in this side, then the tangent vectors of the us are sort of all the time dependence are either in u or in yis. So you replace that information, and ideally in a Finsler geometry, you would have us and u dot s, but you replace this u dot to be with the yi's to be the control functions, and the control functions follow the all the properties of the previous control function of the f gamma was following. So the second argument in this case follows the properties that f gamma was following.
Okay, I think we should pause the recording here and also let Aranya take a break. He will be back. We will start right at 4:30, the next lecture, right on time.
Okay.
So, okay, welcome to the last lecture of today. Aranya will continue telling us about complexity in QFTs. Over to you.
Okay, thank you. So let me write it in this way. We had this expression for a time-dependent unitary. And for our case, where we stay in the time 0 to 1 at t equals to 0, the u0 will be identity, and at t equals to 1, u1 will be our u target. And from this identity, what one can figure out is that yis mi can be written in this form.
What does the p before the exponential
path ordering, what I mentioned as, for example, right to left, I build the circuit from lowest values will act first, and then the highest values or the operators acting on primarily will be the earlier time operators, and then we keep adding the later time operators in the left hand side. Okay. So this can be written in this form. This one can write it in this form. And but what we want to write is a metric in terms of this yi's. So we should have a representation of yi's by themselves. Until we have a representation of the generators of this group, we cannot really generator of this universal gate set, we cannot really get a representation of yi's. So let us try to do so. How do we do that? So the first point to figure out would be, how do we specify the space of states? Let us for now forget about the normalization part. It would depend upon this, what are inside exponential, they will make sure what the normalization is. So we could write this as in this form, where for two oscillators, the relevant space of states are represented through three-dimensional space of 2 cross 2 real symmetric matrices. And we would also need the determinant to be greater than 0, or we could also get away with that. But the specific reference and target state that we have in mind, the reference state is this, and this is a 2 cross 2 identity matrix, and the target state is omega 1 beta over 2 beta over 2 actually, yeah. And for this problem, actually, like we saw, the scaling and entangling gates are enough. So we are not really transitioning the x1 by some particular constant shift or so. We could do that, but the easier way would be to just scale and entangle the two things. So let us fix the gate set to be a smaller one, which we call QAB, for all values of A and B. Here will be 0 and 2, 1 and 2. And so when A and B are equal, they will give us the scaling gates, and when they are not equal, then they will give us the entangling gates. And let us write this as exponential of epsilon MAB, where these will be the generators of the universal gates. So MAB, one can check that it would be of the following form. And in principle, since we have 4 gates, Q11, Q12, Q21, and Q22, we would have 4 aims. So let us call them M1, M2, M3, M4. But they actually will be like 1, 1, 1, 2, 2, 1, and 2, 2. But for this specific case that we are dealing with, is the space, 3-dimensional space of real symmetric matrices. they will act on the A in this way. This is how you find the translating and so if we write this in here, okay, I have kept these indices actually in here, and MAB, the matrix elements for this for generating actually any matrix that can work on these 2 cross 2 real symmetric matrices. We can get away with by simply delta AC and delta BD. They will generate the most general set of matrices, for example the GL2R matrices, and we will work with that choice. So let us choose the generators to be the generators of the GL2R matrices. And as I mentioned, they are, so any general 2 cross 2 matrix acting on these real symmetric matrices can be represented through these generators of GL2R group, but which is actually a 4-dimensional space. So we have a 3-dimensional space of states and a 4-dimensional unitary space. So the geodesics I have been talking about previously, geodesics in the metric should actually be one parameter family, among which we want the one with minimum length.
Aranya?
Yes.
In your previous slide, this
Yes.
QAB seem to act on A's, but A is on the exponential of the wave function, right? And I thought these gates act on the wave function. What am I missing?
These are like now what I have written, these QABs, these are, for example, since I have also changed the, for example, I wrote it somewhere, I suppose. Yeah, for the previous case where this was acting on the MABs, where the scaling or entangling gates were acting on the exponentiated version of the wave function, you would have these kind of generators.
Okay.
And if you simply act on the 2 cross 2 real symmetric matrices through which you represent your space of states, then your generators will be of this form. And your QAB will be any general real linear 2-dimensional 2 cross 2 matrix.
I'm just confused by this statement. This A prime is equal to QAB, A QAB transpose. Would it be MA M transpose, or would it still be QAB A Q transpose?
No. Since we are now the generators are these things, but they are generating the actual unitaries, which are the QABs. These are again not exactly same as the previous Q11, Q22s, and so on. Let me write a tilde upon this, but you would find that this would give you the new transformations, which would transform this 2 cross 2 real symmetric matrices.
Okay. Yeah, I'm a bit confused because the QABs you have written are in fact the QABs you had earlier also.
No, but the MABs were different, right?
MABs were also the same, I think. It's just that you use the commutation between X and P and went from like XAPB or XAPA plus PAXA to this unified form, which is XAPB plus half delta A, IXAPB plus half delta A. And exponential of this was what you had earlier as QAA and QAB.
Yeah, but I think, okay, let me do it. Yes, but that was there still the QABs. The QABs can be same, but they are acting. They were acting at that point on the psi x1 x2.
Yeah, exactly.
Whereas they are acting now on the particularly the 2x2 matrices.
How will that happen? Because that is on the exponential in the wave function, right?
Yeah, so I'm forming the MABs, and you can see, for example, any, let's just use some example, epsilon 0, 0, 0, 1. This should probably give me some, no, 1, 1, 1, epsilon. And this should, when you act with this thing, or say
I think off diagonal entries would still be 0 because you exponentiate the diagonal terms.
yeah, sorry. Okay, this gives me omega, this gives me 0, this gives me 0, this gives me to the power epsilon omega. Again multiply this with 0, 0 to the power epsilon. You get omega naught 0, 0, 0 to the power 2 epsilon omega. This is, so I think the whether you act on like these things or act on like different other gates, for example, with different choices, the this would vary by only a matter of maybe normalization.
Okay, maybe we can discuss on slide.
Yeah.
Sorry.
Actually, I can discuss this later. But this should not be much dependent on this thing, but it is instead of the representation, you should be able to see the space of unitaries as GL2R matrices, and the generators should be considered as I wrote earlier, M11, M12.
Okay, that much I understand. Yeah.
M22. So, and we would have to find the minimal geodesic among the one parameter.
So why are you calling them space of unitaries?
Since they are in the, they are generating the group in which the unitaries stay, right? All the universal quantum gates are in the GL2R group, which can be generated by these generators of GL2R. So all QABs, for example, are the universal gates, and they stay in GL2R.
Okay.
Okay. So now, as what I wrote earlier, del is US U inverses. From this, now you can multiply MI transpose in both the sides. And take a trace. So in the trace, these won't participate, whereas this would give me a identity actually. So in principle, you can write yi of s in matrix representations. If you take the MI transpose of these generators, you would get the trace to be MI transpose to be always 1. And you can write this as therefore trace of del S U inverse S next, what we do is we explicitly construct a GL2R parameterization, which is done by asking that we are looking U belongs to GL2R, and we will construct this as R cross SL2R. They are exactly same. So SL2R has 3 parameters, and this has this will go on. And this is the reason why we get the 1 parameter family of geodesics, this that among which we have to find the minimal one. So we can parameterize the US in this way. With asking that x0 square. Okay, for this one is let's say SL2R unitaries. Which should, of course, as we expect, this SL2R should give us the ADS3 embedding space, the way we parameterize these matrices, with asking that the determinant of U is 1. Again, similar to what Nielsen did, we are asking for a determinant where it is 1. Or you could also, yeah, that would be good. Okay. Since this happens, since ADS3 is the universal cover of SL2R, and we can now go to the global coordinates of ADS3 and choose these as these parameters. But SL2R is not the whole thing. We need an R as well. So to do so, we would, in this embedding space, we would, or here as well, we would represent a new parameter. So the actual unitaries of GL2R, we will represent it in the following way. We would multiply it, the parameter in here. And this would give the embedding space in this way. Where a new parameter is there, which is 2i. And this is how the R is incorporated. Okay. So now using this representation of US, or rather when you write the x0s and x1s of global coordinates of ADS3 as well, you can use that form, and now we are ready to form the metric, which should be simply for example, we will choose for now the GIJ, or we could have written okay, my iPad has gone offline again. Yeah. We could have chosen the, for example, the FQ to be any. Okay, let me write it a bit differently. And ideally, we choose it to be ds squared to be delta ij dyi dyj. This is similar to this one. So ds should be a square root of this one, and so on. So here we replace the dyij's or dy and di using the previously introduced expression, this one. We write them as this. MIT. So you have the previous expression of u in here, where you have to replace the x0s, x3s in terms of these global ADS3 coordinates, and you'd find that if you do that, then the final metric becomes this thing. So you could also make a change of variable, which in the paper Myers and Jefferson they do. They change the theta and tau variables into the light cone coordinates, and in that way you can write it in a new form where you have, say, 2 dy square plus 2 d rho square plus 2 dx square plus 2 cos 4 rho dz square minus 4 cos hyperbolic 2 rho. So once you get to this metric, what you can again check is you have this one formed from the basically using the generators of your unitaries and the representation parameterization of your unitaries, which is this one. Now the right invariance can be again checked in here. The easiest way to check is that if you multiply this US matrix by any general GL2R matrix, whatever GL2R matrix you can multiply, and you would see that this form will be completely unchanged. So the metric remains unchanged under any right multiplication of the unitaries by a GL2R matrix. But if you, on the other hand, if you had multiplied this extra GL2R matrix in the left hand side, LHS, then it would not remain invariant anymore. This you can maybe, this is a nice exercise to check. I have checked it, and it is easy to do in mathematics. So we get to the metric part, and now all that is remaining is to find the geodesics. But to find the geodesics, I will not do that part during these lectures. I will just mention what are the basic things that you need to find the geodesics and how do you find the minimal one. Of course, finding the geodesics, what they use is the killing vectors, symmetries and killing vectors of the things, the metric. So since these are GL2R matrices and they have 4 generators, there is supposed to be at least 4 killing vectors. 3 of them, which you can easily see from these pictures, del Y, del rho, and del X. Or maybe not del rho, actually del theta. Dependence. Del Y, del tau, and del theta. In this one, it so happens. And there are 2, actually there are not 4 killing vectors in here. One would find there are 5 killing vectors. The last one is an accidental symmetry. Which comes purely due to the choice Gij is equal to delta Ij. So which we made at some point. Let me see. Yeah, at this point we went delta Ij, which basically means is that we assign the same cost to every direction. Now this 5, so this accidental symmetry is due to this particular choice that every direction has sort of equal cost, and that introduces a new symmetry in this picture. And the 5 killing vectors, for 5 killing vectors you would have 5 conserved quantities as well, or conserved quantities, and from then you can easily it is easy to find the geodesics using sort of the boundary conditions on the, so let's say we call this vector x of s, which has all the variables. It's basically tau is the coordinates are the rho is, theta is, and y is. Now, since we know that we are at s equals to 0, u is equal to identity, whereas at x equals to 1, we reach the target state. Using that, one can put conditions on this one as well. Primary condition would be the form you had for u in here. You would have to put values of tau, theta, and y and z in such, not z, but tau, theta, y, and rho in such a way so that you get an identity matrix for s equals to 0. That would be x at s equals to 0 would actually turn out to be 0, 0.
Aranya?
Yeah.
So what is the statement regarding this additional killing vector that you are having? Does it allow you to set a Gij equal to delta Ij? I missed that part.
No. Since we are assigning, since we are fixing Gij equals to delta Ij, we are sort of giving, here we could have in principle, since we are choosing this cost functional, more generally one could choose Gij, Yi, Yj. But since we are choosing this Gij to be delta Ij, which is among the valid cost functionals derived in Nielsen's paper, that gives us an accidental symmetry, which is due to delta Ij means that we assign to every gate, we assign the same cost. So I talked about something called penalty factor the other day, which is that if you have, say, 4 gates, A, B, C, and D, or these Yi's or the control functions, you could multiply some numbers with those control functions. Say you multiply a P square, a Q square, and R square with these 3, where these P square, Q square, and R squares are some sort of big numbers, which we call penalty factor, and it simply means that those gates have a higher cost, or whenever you use them, you associate a larger number with the in the metric or the cost functional. You would get a larger number in here. The cost functional, it should keep increasing whenever you add more cost to some gates. But here, while choosing the sorry.
After you set Gij equal to delta Ij, still you are left with this original GL2 symmetry. Is that right?
Yeah. Of course, that has not. This is about just choosing the functional. The GL2R is about the symmetries of the unitaries. Unitaries are in the GL2R space, and you could choose when we choose in this particular cost functional, we can choose in different ways, and we choose this Gij that could be taken in here to be delta Ij, and that gives sort of defines same cost in every direction, which is 1. In Myers and Jefferson's paper, in a later section or in the appendix, they have also dealt with penalty factors, where they introduce different things, then different numbers to each gate, and where the Gij will not anymore be delta Ij, and there the calculations get trickier, and you have to work harder to get the killing vectors and the symmetries. For example, the 5th accidental symmetry won't be there in that case.
Okay, thank
you. Okay, but we find that so we use this thing, as well as we use some values. For example, at s equals to 1, the final case, we use, say, tau 1, rho 1, theta 1, and y1. So given this and the geodesic equations, one can, and as well as the not the geodesic equations, but rather the conserved quantities, they would be eventually be related to sometimes rho 1 dot, sometimes theta 1 dot, and such stuff. So we get that ys equals to simply y1s. There is no constant associated with it. So at s equals to 0, y was 0, and s equals to 1, y1 is simply 1. This is the nature ys, and theta s will be dependent on this delta theta s plus theta 0. Rho 1 is again rho s, dependence on s, again rho 1 s, and tau would be 0 throughout the in the geodesics rather. So, or in rather, tau would be actually what happens is tau 1 plus theta 1, one gets it's to be constant. But in the paper, just let me mention this, in the paper by Jefferson and Myers, they not really explicitly find out the, so we would have, after using all these conserved quantities that we get from the killing vectors, we would have still a 1 parameter family of geodesics, and the picture should look like something. Let me draw it. So this line that I'm drawing is tau 1 plus theta 1 equals to constant line. So it becomes a spiral in this space, and here you have the theta coordinate. So the minimal geodesics could be from here. So theta 0 is, say, here. You could have different ways to you want to find the minimal geodesics connecting these 2 points. So this is the initial point, and this one parameter, this sort of gives you, this can be one geodesic, this can be one geodesic. They are verified by a parameter, and one finds which Jefferson and Myers, they don't show it explicitly. But first they compute the straight line geodesic that is possible in here. And once they calculate, once they have the length of the straight line geodesics in terms of the parameters of the theory, length of the straight line geodesic rather, among all of these one parameter family of geodesics. So they show that by the parametric analysis, so they take different values of it, will depend upon some theta and pi and so on. They take different values of theta and pi. Just give me a moment. So they find the they find the parametric. They use the parametric dependence and take all possible values of, for example, if it depends upon theta 0, all possible values of theta 0 for, and the function they have is sort of cos hyperbolic theta 0 1 minus 1 over 2 sort of. So how, in which range does it lie for different, all the allowed values of theta 0, and so what will be the minimal geodesics? They parametrically like scan the space, and they find that the straight line geodesics is the minimal geodesic indeed. Among the one parameter family. So now the final form of this, of the straight line geodesic, if one writes, one finds that the dut as a function of, since y1 is just a function of y and rho, actually this becomes, this has a form y1 square plus rho 1 square, and they also find that y1 and rho 1 are the ending points, ending point values of the trajectory. Now, simply using this, one can show that 2y1 also in the, along the way, what they find is we will have, once we finalize our boundary conditions, eventually this y1s, rho 1s, theta 1s and tau 1s, we will relate it to the final state, that is omega 1, omega 2, beta, etc. These parameters, and also it will depend upon the reference state, which was omega r, or rather omega 0 probably, and it, the final, this one is the minimal one, the form of which is half of rho omega 1 by omega 0 square. So omega plus by omega 0 square plus log of so the final complexity of this problem boils down to some form where we can write it in terms of the normal mode frequencies. Actually, the form becomes such a comes in such a way of omega 1, omega 2 and beta that we can recast it in simply in terms of the normal mode frequencies and the reference frequencies. And at this point one realizes that after getting this confirmation, which is non-trivial after dealing with all these geodesics in the space that we formed. So I hope this metric construction and right invariance, these things are clear now. How do we form the unitary by parameterizing these things? And we use a new parameter to the power y, after which the metric that we form is right invariant, and we look at the geodesics inside them along with the boundary conditions given by the initial and final state points, through which the information of the state comes in the geodesics or in these coordinates. But at the end, one again finds that the result depends on the normal mode frequencies only. Frequencies and maybe the reference frequencies. So although we needed to realize the problem, we needed to go to the position basis where we could actually have a way to realize the entanglement present in the theory of the coupling between the two oscillators. But the final result is reflected in terms of the normal mode frequencies, where the oscillators are decoupled, the normal mode oscillators are decoupled. So the takeaway from this problem is that any non-trivial, so for example, we dealt with this omega 1, omega 2, beta and beta. This we kept arbitrary. So we used them just as some number. We didn't give any number, and we kept the reference state as omega 0 and omega 0. So any non-trivial transformation in the position space. So from this reference state, one goes to this target state. Can be understood as simply an amplification of the frequency in normal mode space. This is because if we translate this 2 cross 2 coupled or entangled state matrix to normal mode, this becomes some omega plus square and omega minus square. But if we take this to normal mode basis again, so decoupled version to start with, if you take that to normal mode again, it still remains decoupled. So it will remain unchanged. So in the physical basis, we go through an entanglement, and that's why we wanted to go deal with this problem. But it turns out that for any such scenario, everything that you need is, in terms of normal modes, this frequency is just amplified, as well as this frequency is just amplified. So then you would, in normal modes, you would not necessarily need any entangling gates had you been doing with these things in the normal mode, which they, after discussing all these things, they discuss how to translate these generators, for example, these generators to normal mode generators, which will act on the normal mode frequencies, how those generators look and so on. And using this technique, actually, this takeaway message, it is not hard to say, using this takeaway and amplification understanding, the general N oscillator case can also be solved, where the unitaries are typically of the form of GLNR, and you have in the state space, you have N cross N symmetric matrices. State space. And this is space of unitaries. Now, from the understanding that we developed, it is, they show in this in their paper, but I will not go through those details. It has just to do with a few orthogonal transformations through which you can realize the generators in the normal mode basis, starting from the generators in the physical mode basis, and so on. And it will not, it's not at all hard to just through some calculations of use, including the orthogonal matrices called as some RTs and R, so on, which are orthogonal matrices. They have, what they showed is simply you would write the general expression in the normal mode basis. Again, in case of N oscillators, it will just be log of omega k over omega 0 square, where these omega k's are the normal modes for general N oscillators. And the omega k's can be figured out simply by discrete Fourier transformation, after doing which one finds that in terms of the deltas or the lattice spacing that we had, that we would have in case of n-dimensional generator. I will write what delta is by k over n, where the Hamiltonian that is dealt with is simply the Hamiltonian that we wrote earlier, is p a square plus omega a square x a square plus x a minus x a plus 1. And they choose, at this point, they choose a periodic boundary condition that the nth oscillator would be same as xa. So omega equals to, and also these parameters. So in terms of this delta, I have written here, and this m, by using discrete Fourier frequency, discrete Fourier transform, it is one is able to calculate the general normal mode frequencies for an in oscillator case, and the same thing can be continued to a d-1 dimensional situation. This was still a one-dimensional string of n oscillators. Let this of n to the power d-1 oscillators, where C is simply half of okay. Yeah. We have to re-log in. Where instead of previously we were taking sum of simply 1k vector momentum mode, here we would have to the ki's form a d-dimensional vector space, so element of a d-dimensional vector. And we have to take all such combinations, and even there the general expression remains the same. So the point that I would like to end this part is simply one can define in this case in the number of oscillators in terms of L and lambda, where L is the total length of the 1D oscillators, and then n to the power d-1 would be simply volume over delta to the power d-1, where volume is simply L to the power d-1. This is the number of oscillators, and in the in this expression as well as in the previous one in the 1D, the sum over k's mean sum over k means we have to perform an integral over all spatial momentas of each of the oscillators. And from perspective of QFT, we know that in the since we have this lattice spacing as our UV regulator, this omega k's or the frequencies will be in the result will always be dominated by the 1 by delta contributions in those omega k's. Since we have the form of omega k is like this one, omega k would still be of the order of 1 by delta. This will always be the dominant contribution in there. So if using this understanding one goes on, one finds that the C becomes in this limit simply V over delta to the power d-1 to the power half, and this half is simply comes due to our choice of cost functional. F2, which was this root over yi square. So this root translated into is translated into this one, and if we can get rid of this root, the dominant contribution can be approximated as v to the power delta v over d delta to the power d minus 1. And once Orpitadi is done talking about the complexity in gravity, this is a similarity that one finds using the cost functional, another cost functional. This is get another cost functional F1, and this matches with the leading behavior that one gets in case of results from holography or gravity. But this is a very, very rough form of the result, very much simplified. The actual form would be this one. So it is also not very reasonable to ask for getting similarities, ask for similarities between a free scalar field theory and a black hole or ADS black hole, which is dual to a strongly correlated or strongly coupled field theory. But this amount of similarity is got by this study. But all of these, there are a few things that all of these are done and valid for Gaussian states only. So whatever you have dealt with, they are the psi, whatever wave functions that we have dealt with, for example, psi 0, x1, x2, or psi reference x1, x2, or psi target x1, x2, or whatever till date, the kind of wave function that this problems, this kind of formalism can deal with are only factorized Gaussians are your typical reference states, and target states also have to be Gaussian states. So these unitaries can only take you from one Gaussian state to another Gaussian state. Also, these are very specific to pure states. And so this part is what I thought I'd discuss from the Jefferson-Myers paper. And since I mentioned the pure states, now let us talk about how can we compute something, how to compute in mixed states when we don't have a state representation, or all we have is a density matrix. Okay, so this part I'll again go back to the usual quantum information side once. There's something known as Schmidt decomposition there in the quantum information literatures. Where any pure state psi of a composite system AB. So A and B, you can from the state you can divide the degrees of freedom in two parts, A and B. Maybe there are 100 oscillators and you concentrate on one of 100 qubits, and you can take 30 to be one, and you could compute call them to be the A and the other 70 to be the B, and so on. Then there exists orthonormal states IA, which belong to A, and IB, which belong to the degrees of freedom B or Hilbert space B, such that you can write this pure state as lambda I, IA, product IB. But this is not a product state. You see, you have all summation over I outside this thing. So all of the basis states in both of the cases, however dimensional those the composite state is, you can, this is known as the Schmidt decomposition, where the constants are for this state to be a normalized one, you need lambda I square, sum over lambda I square to be 1. Lambda I is greater than or equal to 0, and they belong to positive real number. These are known as Schmidt coefficients. Now,
We seem to have lost Aranya.
Does anyone know why the lambda should be positive?
okay. Am I audible?
Yeah, I don't know. Lata actually asked a question while you were away. She asked that
Yes.
why the lambdas should be positive.
I'm just asking if you have, do you have any intuition about
This sort of I took as definition. This might have some proof, and I think Subbu might be able to comment on this. Is he here? But this the positivity of lambda we won't need. So
yeah, I'm just curious.
yeah, I would look into it and let you know. So from this decomposition, at any point you can say form a density matrix, which would be simply ij lambda I lambda j. Okay. And if you want to say, as we talked about this composite system A, you can get the rho A to be simply lambda I square IA and rho B to be where these lambda I squares are same for both rho A and rho B. And if it is this psi is a product state of this two systems A and B, you would find that this rho A and rho B would be simply pure states. So you can calculate the trace of rho A square and you will find it to be 1. Now going to the purification side, what we can do is the other way around what we just did. It would be doing a thing which is just the other way around.
Aranya,
Yeah,
there's just
yeah.
one question that usually, yeah, in your previous slide, usually we talk about, yeah, maybe you're doing that, but usually what we do is in purification is we have some state psi, which could be a mixed state or any state, and then you make psi cross psi, you take the two.
Yeah, actually not psi, I will just do that.
But
yes.
but here in the in the previous slide you started with a pure state, right? For
Yes,
which
yes,
you
I'm
talked
still
about Schmidt
doing.
decompositions.
Yeah, I'm still doing a pure state thing. Just this Schmidt decomposition will be similar when in the just next slide I will do a mixed state.
Okay, so
yes.
Okay.
I'll just do this. Okay, so let us start from if we start from a rho m for which we don't have the typical state representation. The only thing that we have is density matrix. Psi, we don't have any psi representation. We can write it in terms of, for example, outer products of the basis states, but there is no way of writing actually a psi kind of representation for any mixed state. So purification is, the idea of purification is that it is possible to construct a pure state MP which has a Kate representation by itself by adding or slash introducing another system P, which let's call this the purifying system. We get some, as I told, we get this MP state, and once the, so for this MP, rho MP will be outer product of two such states, and if we let me say rho m, first to take trace over the P region, you would get back a rho m which is same as this rho m. So how is that constructed? So this purifying system that I was talking about is also sometimes called fictitious or ancilla system. And say we start with, for example, in the Schmidt decomposition, we said that rho A and rho B would be having this kind of representation starting from a pure state. Again, say we have for this mixed state rho M, we have as orthonormal decomposition similar to what we wrote for this decomposition case is sum over I. So this PI is similar to what we had in case of Schmidt decomposition, the density matrices we had there, it was rho I square, and so PI equivalent to rho I square. In case of Schmidt decomposition, after tracing out, we would always get a mixed state unless the pure state that we started with, which was this, is a product state. And in that case, this rho A it can be written in terms of some simple psi. We don't need to introduce these lambda i's. There can be a single lambda, which is 1. But in this case, if we have more than one lambda i's, this looks equivalent to this thing. And in the same way, it's just the reverse problem. The purified state would be defined like is usually defined by adding this P, which has the only assumption that these people made, which has same space, same state space rather issue as M. So there, the statement is that the new state MP can be represented as in this way. EI. Now again, since we had this analogy of Pi being similar to lambda I square, this now becomes similar to lambda I, and we get to the pure state that we started with in case of Schmidt decomposition. For example, this is similar to lambda I, IA, IB. Okay, you can check that starting from this, and if you now trace out the P part, then you would get back this rho M again. Okay, so how does one compute or take these ideas to the free scalar field theory computation? Let us talk a bit about it. And so what we do is start from Hamiltonian, again a similar Hamiltonian that we had earlier. Say that, okay, so this can also be again written in terms of the lattice operators, and we can write it in the following form by going to 1 from n, half of pi n square plus half of pi n vn prime by n prime. I will come to what I mean by this n and primes. Here should be n. So what we define is first we define the lattice in the following way: x equals to a n, where a is the lattice spacing, and n is the position of each site. Say you start from 1, then you'd be at point A, then 2A and 3A and so on. Now the discretized scalar field, which I have already done here in this part, at nth site is represented by simply phi n equals to phi field at Na. Similarly, pi will be defined by A into the field pi at Na. And this phi n and pi n follow the usual commutation relation. Okay, now another thing what is done is the periodic boundary condition is introduced. Once again, similar to the d-dimensional case that we are handling before, phi or n oscillator case where phi n plus n equals to phi n, and similar for phi n plus n equals to phi n. In this form, if I go back to this slide, here I have written this VNN prime. This actually can be written to be of this form. Inverse square m square plus 2 cos 2 pi k. This cos 2 pi k over n 1 over 1 minus cos 2 pi over n is simply again what we had, like 4 sine square pi k over n we had in case of n oscillators while dealing with the free scalar field theory problem for n oscillators in Jefferson-Myers case. I'm just writing it a bit differently, but this won't matter much. So the final expression, this whole thing is multiplied by 2 pi I k n minus n prime over n. And the psi 0 or the wave function can be found out from this to be n0 exponential. Again, going to normal mode and doing usual things, where instead of where we have this n capital N dimensional vector in here, the W n n prime, this matrix is 1 over n k is equal to 1 to n square m square plus again this thing, just this part of the whole thing comes in. And now let's say we start from n number of oscillators, a very huge number of oscillators, say n equals to 10,000 or whatever big number you can have. Literally, this problem is going to boil down to a numerical problem. So it might not be always, one might not be able to take very large number and have the results in Mathematica. So what we do is typically you trace out a huge number of sites from this one. Say to begin with, we trace out 9,999 sites from this, and this can be done by, for example, once from a paper by Bombelli called, which is the famous known paper, Quantum Source of Entropy for Black Holes, or something. In that paper, these things are done in details. And so from this psi 0, what I mean is this psi 0 can also be written if you have two systems. Say if you divide this whole system into 9,999 plus 1, you can divide the space as well. For example, in the previous expression, I had this as n-dimensional vector. Now I would write this as phi a, phi b t, and p q q transpose r, phi a, So this is sort of, this is for 1, this would be a simply 1 element. This would be 99 elements. This would be 1 element. This would be 1 cross 99. This would be 99 cross 1, and so on. So this whole matrix can be divided into such blocks, and one can also, for the, if you trace out say this region, let's call this B and this to be A, then rho A you can calculate in terms of, you can have an expression of rho A in terms of these elements. The way of writing which is simply exponential minus of half phi A prime. Okay, let me just write this. Here this matrix would be represented by P minus half Q R inverse QT minus half Q R inverse QT. Okay, sorry for the interruption, the thing has again stopped. I'll just be back in a minute. And I'll only need up to 6 p.m. today to complete.
I don't know if you need 5 more minutes extra, that's okay. That's not a problem.
I think I'll not be anyway able to start something new today. So after ending this, that would be fine.
Okay, whenever is the natural stopping point for you,
Yes,
you decide.
Yes. Okay. And finally, T minus half QR inverse QT. So given such a block diagonal form in this part of the matrix, in the exponentiated part, one can point out in terms of those blocks, one can write down the density matrix for any given A. And so you now have, typically this is unless your state is coupled or unentangled state, you would get this to be a mixed state density matrix. So now you want to go back to a for this mixed state, you want to calculate the complexity. The way it is done is, of course, purification, and is known as, let's say, complexity of purification. I'll denote it by COP. So you add again ancilla systems with the condition that when you trace out the ancilla, you would get back rho A. Now, given the number of degrees of freedom of the system A, for example, if I started with 100 oscillators and in A I have, say, 1 oscillator, then from the Schmidt decomposition or Schmidt decomposition based purification ideas, one firstly takes the minimal thing to add would be another 1. So instead of adding 99 new oscillators, which is the system B, you add simply 1 ancilla and you try to find with a matrix for which you would, after tracing out this ancilla, you would get back the same rho A. So let's say we try starting from this rho A, we form the purified state, which is psi AB of phi, which is again written as some normalization which will be dependent upon these things, and minus phi t b phi, where t equals to yeah, t equals to AB. So in the same way that we did for the earlier situation, in here from this part we could say that the density matrix will be of this form. We can again use this thing and say that this is say minus half phi a phi b prime j k q t, and then again this would be transpose. Okay, so let's say this is the wave function for this. Again, we can write the wave function for this purified state, but we don't know now all the elements of this matrix. For example, since this again corresponds to the A part, so this will be of the dimension of A. This is the dimension of B, and these are like A cross B and B cross A dimensional matrices. And from this again, if you trace out B, then your rho A, say after purification, should have this everything exponentiated minus phi A prime, and so on. But now you will have this in terms of JQR minus 1, not Q, rather. K inverse, K transpose, and so on. So you'll have similar things that we had here in case of actual tracing out. And so you have to, what you have to do is match the matrices. For example, this J matrix has to be this, you know exactly. This is a known matrix which is coming from the subsystem that you know. You don't know this matrix and you don't know this matrix. These are what you have to figure out. So this will be equal to, this has to be equal to P, which was when we had this whole AB system, the pure state that we started from. And you have to match these things. So J will be equal to P, and the other things that will have to follow. Among this K and L matrices, you would have all these kinds of, you would have to satisfy this thing. So this part you suppose you know, since this is the 100 oscillator state that you exactly knew, and you have, so when you define the this matrix for say, you keep some unknown parameters in this K and KTs and L and so on. So of course this matrix has to be symmetric metrics as we have seen in case of the usual complexity calculations. So there are some constraints which you can use to get rid of some parameters, but otherwise you have to keep a few parameters, and for different cases you have to minimize over those parameters to get the complexity. So there can be infinitely many choices of values of the parameters in unknown matrices K and L. So, but you can, so you have this state or psi AB and this matrix. You can, given this matrix, you can calculate the complexity from a plus V prime. This should be V prime. So A plus V prime, the number of dimension to which you have purified the system. For example, you have purified, let's say you have purified to 1 plus 1. Then you take a two-dimensional or two oscillator kind of scenario and such a reference state and go to this new reference state. So you would write the complexity function and minimize over all these parameters. This is therefore a numerical problem. Some part of it has been covered analytically by Chapman, Myers, and there probably the paper came in 1909. It's known as complexity for mixed state. But what they do by analytics, they have both analytics and numerics, but they have mostly used numerics in a different way. So what else you could have done is you could vary many things. For example, you could vary the delta or the lattice spacing that you have in the theory, in the starting theory of 100 oscillators. Variables that can be changed in the starting pure state. Note that this is not the reference state in this case. The reference state is dependent on to which dimension do you purify the system to. So you have this 100 oscillators. That would not be the dimension of the reference state. If you get to 1 or maybe 2, then if you double the degrees of freedom to introduce the purification, then your reference state would also be 2-dimensional, and for this case maybe 4-dimensional. You could vary the M, you could vary this number of oscillators that you started with. And the other non-trivial thing to check is that although during firstly mentioning purification from the side of quantum information, I mentioned that the new state or the ancilla state has to have the same state space. But in principle, one could ask that for at least this complexity of purification, that how does complexity behave in case of purification? Should we stop at, for example, we have a reduced state of one oscillator. Should we stop at 1 plus 1, that is 2 oscillators, is that essentially my work is done, or should I also check for adding, instead of 1 I can add 2 oscillators and I can also get to a pure state in that way. So the total state is of 3 oscillators. We have to make sure that the thing is one of the two among one of the two of the following. So either this has to be the complexity for, I would call C2P, where you, or rather C1 plus 1P. You had one state, you take another state and purify, the complexity of purification. Is it lesser than 1 plus 2P, when you had one state but added 2 state and purified? If it is, then this purification is indeed the minimal purification that you could have reached. Otherwise, but it is a job to check. Also for C2 cases, so your reduced system is for 2. You have to check whether the 1 to plus 1 purification is greater than 2 plus 2 or not. So ideally for 2 system you are supposed to add 2 more, but you have to check whether just getting to a pure state by adding 1 is not the complexity of purification. Indeed this one is. Also you have to make sure that you go towards both sides. This has to be the minimal one, C2 plus 2 or C2 plus 3. Not really when I say make sure or things, I have to check. I should say that you have to check that whether this is the minimal one. Otherwise, for it could be that for complexity, the minimal thing could be C2 plus 3 instead of C2 plus 2. So all of these things have to be checked, and there are some things that Chapman and Myers paper, they dealt in a simplified way. They only dealt with this 1 plus 1 and 1 plus 2 case, and for the any higher reduced system case, they did something called mode by mode purification. So if say you have this number of degrees of freedom in your reduced state, you could purify it in 2 ways. You could add the same number of ancilla qubits and purify completely, or you could add at a time 1 ancilla qubit for each of them and purify each of those modes. So they, due to numerical difficulties, they compute only this one, this mode by mode purification scenario, and only for 1 plus 1 case, they say that whether 1 plus 1 to probably 2 plus 1 case, they say whether mode by mode purification holds good for a particular subset, or at least particular subset of purifications. It given some conditions, mode by mode purification is a good way to purify a system, but the general way should be to purify this through by adding a copy of the whole system, which is also numerically challenging. But a few recent papers came in last few days, mostly by Eric Tony and his collaborators, recent paper. So Tony, this is my last slide and I will just state this. Tony has found some better analytic way using Fisher metric to compute, or slash, I should say, give a better understanding of complexity of purification. Okay, so I'd stop at this point. If anyone of you has any question, you can ask me.
So first, let us all unmute ourselves and thank Aranya for this wonderful series of lectures.
Thank you.
So if anyone has any pressing question, please go on. Okay, if not, let us thank Aranya again.
Okay. So if I get some more time in the last lecture, maybe I'll just talk about, since Shubhamda was asking the other day, I'll maybe talk about briefly what understanding has been developed in the CFT side. One or two paper has just arrived in last 2 or 3 months. If I get some time, I'll just talk about very briefly about those calculations.
Yeah, sure. I mean, that's really up to 3 of you.
Yes.
And also, I mean, even if it so happens that you don't get any time, I can always recommend that please share it on the Slack so that people can read up on it and have discussions.
Sure.
So let me stop the recording, and if people have any further informal discussions to have, they can go ahead.